You walk into a room with a clear purpose in mind. Maybe you're grabbing your phone charger or looking for that book you were reading. But the moment you step through the doorway, it's gone, completely blank. You stand there, scanning the room, trying to remember why you came in the first place. That frustrating experience has a name: the doorway effect. The doorway effect is a cognitive phenomenon where passing through a doorway causes you to forget what you were about to do. It's not just you being forgetful or distracted. It's actually how your brain organizes and stores information. Research suggests that our minds use physical spaces as mental filing systems, creating distinct memory episodes tied to specific locations. Here's what happens. When you're in one room, your brain encodes memories and intentions within that spatial context. The kitchen becomes associated with making coffee. Your bedroom links to getting dressed. Your workspace connects to whatever project you're focused on. These aren't just neutral backdrops. They're active parts of how your brain structures experience. But when you cross a threshold into a new space, your brain interprets this as a transition point. It's like closing one chapter and opening another. The previous context gets filed away, sometimes a bit too efficiently. Your intention to grab that phone charger. It was part of the previous episode, the one that belonged to the room you just left. This effect was first documented by researchers at the University of Notre Dame. In experiments, participants navigated virtual environments, memorizing objects and moving between rooms. Consistently, people forgot more when they passed through doorways compared to walking the same distance within a single room. The doorway itself acted as what psychologists call an event boundary. Event boundaries are moments when your brain decides one experience has ended and another has begun. They help us organize continuous experience into manageable chunks. Without them, life would be an overwhelming stream of undifferentiated information. But the trade-off is that these boundaries can sometimes work against us, filing away information we still need. The effect isn't limited to physical doorways either. It happens in virtual environments, and even occurs when people mentally imagine moving through spaces. What matters is the cognitive shift, the sense that you've entered a new context. Some researchers have found that even significant changes within a room, like moving from one distinct area to another in an open floor plan, can trigger similar forgetting. Interestingly, the doorway effect reveals something deeper about how memory works. We don't store experiences like computers store files, in neat, unchanging packets. Memory is dynamic, context-dependent, and deeply tied to our physical environment. The same information can be easier or harder to recall depending on where you are and what mental state you're in. There's also a connection to something called location-dependent memory. Students who study in the same room where they'll take a test often perform better than those who study elsewhere. The physical environment becomes woven into the memory itself, acting as a retrieval cue. When you're in that space again, the memories tied to it come back more easily. So what can you do about it? One strategy is to mentally rehearse your intention as you walk through the doorway. Actively thinking, "I'm getting my phone charger," while crossing the threshold can help keep that purpose active in your working memory, preventing it from getting filed away prematurely. Another approach is to use the effect deliberately. If you're stuck on a problem or feeling mentally stagnant, physically moving to a different room can help reset your thinking. The same mechanism that causes forgetting can also promote fresh perspectives and creative problem solving. The doorway effect reminds us that our minds are embodied. We don't think in isolation from our physical surroundings. The spaces we move through actively shape how we remember, what we forget, and even how we think. That annoying moment of standing in a room, wondering why you're there, isn't a bug in your mental software. It's a feature, one that helps organize the constant flow of experience into something your brain can actually manage. Say a word out loud. Now say it again, and again. Keep going, maybe 10 or 15 more times. Bowl, 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 bowl. At some point, something strange happens. The word stops sounding like a word. It becomes a meaningless noise, a collection of sounds with no connection to the round object you eat cereal from. That bizarre experience is called semantic satiation. Semantic satiation is the phenomenon where a word temporarily loses its meaning when you repeat it over and over. It's not that you've forgotten what the word means. It's more like the connection between the sound and the concept has short-circuited. The word becomes unfamiliar, almost alien, even though you've known it your entire life. The effect was first described in detail by psychologist Leon Jakubowicz James in 1962, though people had noticed it informally for much longer. James used the term semantic satiation to capture the idea that the meaning of a word gets exhausted through repetition, like a muscle fatigued from overuse. But what's actually happening in your brain? The leading explanation involves neural adaptation. When you perceive a word, specific neurons fire in patterns that represent both its sound and its meaning. These networks light up consistently each time you hear or say the word, but neurons, like muscles, can tire. When the same neural pathway fires repeatedly in quick succession, the neurons become less responsive. They essentially need a break. This temporary fatigue affects the semantic network, the web of associations that give words their meaning. When those connections weaken, the word loses its conceptual anchor. You're left with just the phonetic shell, the raw sound, disconnected from what it represents. It's like seeing a familiar face but being unable to remember who the person is. The recognition is there, but the deeper connection has temporarily vanished. Semantic satiation doesn't just happen with spoken words. You can experience it with written words too, especially if you stare at one word for an extended period. The visual pattern starts looking strange, the letters seeming to float apart or lose their coherence. It's the same underlying mechanism, just triggered through a different sensory channel. The effect is usually brief. After a short break, anywhere from a few seconds to a minute, the neural pathways recover and the word regains its meaning. It's a reversible fatigue, not permanent damage. But in that moment of satiation, it can feel genuinely disorienting, especially with words you use constantly. Interestingly, semantic satiation reveals how fragile our sense of meaning actually is. We tend to think of language as stable, solid, with words firmly attached to their definitions. But this phenomenon shows that meaning is an active process, something your brain constructs moment by moment. It's not stored in the words themselves. It's generated through neural activity, and that activity can be disrupted. Researchers have used semantic satiation to study how the brain processes language and meaning. By inducing the effect and then testing reaction times or association tasks, scientists can map which cognitive processes are affected and which remain intact. For example, semantic satiation reduces your ability to quickly judge whether a word is related to another word, suggesting the conceptual network is impaired. But it doesn't affect your ability to recognize the word as a valid word versus a nonsense string of letters. The phenomenon also connects to broader questions about consciousness and perception. If something as fundamental as the meaning of a word can dissolve through simple repetition, what does that say about the stability of our experience? It suggests that much of what feels solid and real is actually a construct, actively maintained by ongoing neural processes. When those processes falter, even temporarily, the construct can fall apart. You can try this yourself right now. Pick any common word, fork, window, purple, whatever comes to mind. Say it aloud 20 or 30 times, as fast as you can. Notice when it starts sounding weird, when the meaning begins to slip away. It's a small, harmless glimpse into how your brain builds the experience of language, and how easily that construction can be temporarily undone. Semantic satiation is a reminder that meaning isn't inherent. It's something we generate continuously through neural activity that can tire, adapt, and need rest. Language feels effortless, but it's actually a complex performance, one that occasionally glitches in fascinating ways. You're alone on a mountain, exhausted on the edge of survival, or maybe you're adrift at sea, waiting for rescue that might never come. In these moments, something extraordinary sometimes happens. You sense a presence beside you, not imagined but felt. A companion who wasn't there before, guiding you, encouraging you, helping you survive. This is the third man factor, The third man factor describes the experience of feeling an invisible presence during life-threatening situations. It's been reported by mountaineers, explorers, shipwreck survivors, and people in extreme isolation or danger. The presence is often described as comforting, protective, even guiding. It doesn't speak in a conventional voice, but its intentions feel clear. Keep going, you'll make it through. The phenomenon gets its name from a line in T.S. Eliot's poem, The Waste Land, which references the disciples on the road to Emmaus who felt a third presence walking with them. But the modern understanding comes from stories of survival against impossible odds, where people consistently report this strange, helpful companion. One of the most famous accounts comes from Ernest Shackleton, the Antarctic explorer. During his 1916 crossing of South Georgia Island, after his ship Endurance was crushed by ice, Shackleton and 2 crew members made a desperate 36-hour trek through unmapped mountains. Later, all 3 men independently reported feeling a fourth presence accompanying them, someone unseen but undeniably there. Shackleton wrote, "It seemed to me often that we were 4, not 3. This wasn't an isolated case. Mountaineers climbing at extreme altitudes, where oxygen is scarce and the body is pushed to its limits, have reported similar experiences." Reinhold Messner, one of the greatest climbers in history, described sensing a presence during a particularly grueling descent. September 11th, survivors trapped in collapsing buildings reported feeling guided by an unseen helper. Solo sailors, lost hikers, even astronauts have described versions of this phenomenon. So what's happening? The scientific explanation centers on the brain under extreme stress. When you're in a survival situation, your brain is operating in crisis mode. Resources are limited, oxygen might be scarce, stress hormones flood your system, and cognitive functions begin to break down in specific ways. One theory points to the temporoparietal junction, a brain region involved in distinguishing self from other and in processing spatial awareness and bodily sensations. Under extreme stress, this region can malfunction, creating a sense that there's another person nearby. It's not a hallucination in the traditional sense. It's more like a misattribution, your brain generating a sense of presence from its own distress signals. Another explanation involves something called bicameral mind theory, though this is more controversial. The idea is that under stress, different parts of the brain might communicate in unusual ways, creating an experience that feels like guidance from outside yourself, when it's actually an internal process externalized. There's also a psychological component. In desperate situations, the human mind seeks comfort and motivation. The presence might be a coping mechanism, a way for the brain to rally its own resources by creating the feeling of support. It's easier to keep going when you feel like someone's with you, even if rationally you know you're alone. Religious and spiritual interpretations have existed for centuries. Many cultures describe guardian spirits, angels, or ancestors who appear in times of need. The third man factor might be a neurological phenomenon, but that doesn't necessarily exclude spiritual dimensions, depending on your worldview. The experience feels profoundly real to those who have it, regardless of the explanation. What's particularly interesting is how consistent these reports are across cultures, time periods, and types of crisis. The details vary, but the core experience, an unseen, helpful presence, appears again and again. This consistency suggests it's rooted in fundamental aspects of how the human brain responds to extreme threat. Some researchers argue the phenomenon has evolutionary value. A brain that can generate a sense of companionship and encouragement during isolation might be more likely to persist through danger. It's a form of psychological self-rescue, an internal mechanism that prevents giving up when survival is still possible. The third man factor challenges our assumptions about consciousness and perception. It shows how the brain, under pressure, can create experiences that feel entirely external and real, yet originate from within. It's a reminder that our sense of what's out there versus in here is more fluid than we typically recognize. For those who have experienced it, the third man factor is often described as one of the most profound moments of their lives. Whether you interpret it as neuroscience, psychology, or something beyond, the phenomenon reveals the extraordinary lengths the human mind will go to in order to survive. You're sitting at your desk and suddenly a brilliant idea hits you. It feels original, fresh, completely your own. You develop it, maybe share it, build on it. Then weeks or months later, you encounter something familiar. A book you read years ago, a conversation you'd forgotten, a movie you watched once. And you realize with a sinking feeling, your original idea wasn't original at all. You've accidentally plagiarized yourself, or more precisely, a forgotten memory. This is cryptomnesia. Cryptomnesia is a memory error where a forgotten memory returns without being recognized as a memory. Instead, it feels like a new thought or original creation. The term combines the Greek words for hidden and memory. It's memory masquerading as novelty, a ghost from your past presenting itself as inspiration. This phenomenon isn't about intentional copying or deliberate theft. It's genuinely unintentional. The person experiencing cryptomnesia has no awareness they're recalling something rather than inventing it. The memory has been stored, but the context, the when and where you encountered it, has been stripped away. What remains is the content, floating free, feeling like it emerged from your own mind. Cryptomnesia happens because of how memory works. When you encounter information, your brain encodes two things: the content itself and the source, what psychologists call source memory. Over time, these two elements can become disconnected. The content remains accessible, but the source fades. When you later recall the content without the source information, it can feel like an original thought because you've lost the memory of where it came from. The phenomenon has caused real-world problems, particularly in creative fields. George Harrison's song "My Sweet Lord" was found to have unintentionally copied the melody from "He's So Fine" by the Chiffons. Harrison didn't deny the similarity, but claimed he hadn't deliberately copied it. The court case became a famous example of cryptomnesia in music. Harrison likely heard the song years earlier, forgot about it, and then the melody resurfaced as what felt like his own creation. Writers face similar risks. An author might write a scene, character, or plot twist that feels original, only to discover later it closely resembles something they read long ago. The risk is higher when you consume a lot of content in your field. The more you read, watch, or listen to, the more potential source material sits in your memory, ready to resurface without attribution. But cryptomnesia isn't limited to creative work. It happens in everyday life too. You might suggest a solution to a friend's problem, feeling clever, only to have them point out they told you about that exact solution last week. Or you might recall a childhood memory as your own when it actually happened to a sibling, and you constructed a false memory from their story. Research into cryptomnesia often uses experimental setups where participants generate ideas in groups, then later are asked to recall which ideas were theirs and which came from others. Consistently, people misattribute others' ideas as their own, especially after a time delay. The longer the gap between initial exposure and recall, the more likely source information is lost. The phenomenon reveals something important about creativity and originality. True originality might be rarer than we think. Much of what feels like original thought is actually synthesis, recombination, and transformation of things we've encountered before. The line between influence and cryptomnesia can be blurry. All creative work builds on what came before. The question is whether you're aware of the connection or not. There's also a social dimension. In brainstorming sessions, people often present others' suggestions as their own, not out of malice, but because they genuinely can't remember who said what. This can lead to tension and accusations of idea theft when the reality is just faulty source memory. Preventing cryptomnesia is challenging because you can't remember what you've forgotten. One strategy is to keep detailed records of your sources and influences. Writers often maintain reading logs. Musicians document their listening. When you later have what feels like an original idea, you can check whether you've encountered something similar before. Another approach is to embrace the reality that most ideas are combinations of existing elements. Instead of claiming pure originality, acknowledge influences and inspirations. This doesn't diminish your work. It situates it within a larger conversation, which is often more honest and interesting than claims of creating something from nothing. Cryptomnesia reminds us that memory is reconstructive, not reproductive. We don't play back experiences like video recordings. We rebuild them, and in that rebuilding, details get lost, including the crucial detail of where the information came from in the first place. Your mind is full of hidden memories, waiting to resurface and surprise you with ideas you think are new, but are actually old friends you've forgotten you ever met. Imagine tasting a word, not metaphorically but literally. The word table tastes like eggs, the name Derek tastes like earwax, or picture seeing sounds as colors where a trumpet note appears as bright orange and a cello sounds like deep purple flowing through space. For most people, this sounds impossible, even absurd. But for individuals with synesthesia, this is everyday reality. Synesthesia is a neurological condition where stimulation of one sensory pathway automatically triggers an experience in another sensory pathway. The most common form is grapheme color synesthesia, where letters and numbers are perceived as inherently colored. The letter A might always appear red, B might be blue, and these associations remain consistent throughout a person's life. The word synesthesia comes from Greek, meaning together sensation. It's not a disorder or illness. It's a different way of experiencing the world, one that occurs in about 4% of the population, though estimates vary. Many synesthetes don't realize their experience is unusual until they discover others don't share it. They grow up assuming everyone sees numbers as colored or tastes words, and learning otherwise can be genuinely surprising. There are many types of synesthesia. Chromesthesia involves hearing sounds as colors. Music might create vivid color displays, with different instruments, pitches, or timbres producing distinct hues. Some synesthetes describe concerts as overwhelmingly visual experiences, with colors dancing and shifting in response to the music. Lexical gustatory synesthesia causes words to trigger taste sensations. This can make reading or conversation into a constantly gustatory experience, sometimes pleasant, sometimes not. Imagine trying to have a serious discussion while every word creates a different flavor in your mouth. Ordinal linguistic personification gives numbers, letters, or days of the week distinct personalities and characteristics. The number 7 might be shy and introverted, while 3 is cheerful and outgoing. Wednesday might feel responsible and serious, while Friday is playful and energetic. These aren't arbitrary associations. They feel inherent and unchangeable. The neurological basis involves cross-activation between adjacent brain regions. Sensory processing areas in the brain are organized in a specific pattern, and in synesthetes, there's increased connectivity between regions that are normally more separated. For example, the area processing numbers sits next to the area processing color. In grapheme color synesthesia, these regions communicate more than usual, causing number perception to automatically activate color perception. Research using brain imaging has confirmed this. When synesthetes see numbers or letters, both the expected visual processing areas and color processing areas light up, even when the stimuli are black and white. This isn't imagination or learned association. It's automatic, involuntary, and rooted in brain structure. Interestingly, synesthesia often runs in families, suggesting a genetic component. It's also more common in creative professionals, artists, writers, and musicians, though it's debated whether synesthesia causes creativity or creative people are simply more likely to notice and discuss their synesthetic experiences. Some famous synesthetes have credited the condition with enhancing their work. Composer Franz Liszt reportedly confused orchestra members by asking them to play a little bluer or make a passage more pink. Physicist Richard Feynman described seeing equations in color. These aren't metaphorical descriptions. For them, the sensory crossover was literal and useful. But synesthesia isn't always convenient. Imagine finding someone's name unpleasant because it tastes bad, or struggling to focus on music because the colors it produces are distracting. Some synesthetes describe sensory overload in environments rich with triggering stimuli. There's also debate about whether synesthesia can be acquired. Some evidence suggests drug use, particularly psychedelics, can produce temporary synesthetic experiences, and in rare cases, brain injuries or strokes have led to new synesthetic perceptions. This suggests the pathways for sensory crossover might exist in everyone, just inhibited or inactive in most people. Philosophers and psychologists have used synesthesia to explore deeper questions about perception and consciousness. If different people perceive the same stimulus so differently, what does that say about objective reality? Synesthesia demonstrates that perception is constructed by the brain, not simply received. The world doesn't come pre-colored, pre-flavored, or pre-packaged. Our brains create those experiences, and different brains create them differently. Synesthesia challenges the assumption that we all experience the world in fundamentally the same way. It's a reminder that consciousness is deeply personal, shaped by individual neurology in ways we're only beginning to understand. For synesthetes, the merging of senses isn't a curiosity. It's simply how the world is, a reminder that reality is always filtered through the unique architecture of each individual mind. You tell a lie. Maybe it's small, maybe it's significant, but as the words leave your mouth, something shifts. Your body knows. You might feel your heart rate increase, your palms get clammy, or a slight warmth spreading across your face. But here's something you probably didn't notice. Your nose just got warmer, and technically, microscopically, it got slightly larger. This is the Pinocchio effect, and it turns out the classic fairy tale wasn't entirely wrong. The Pinocchio effect is a physiological phenomenon where lying causes a measurable increase in temperature around the nose and in the orbital muscle area around the eyes. When you lie, your body experiences stress, even if you're a practiced liar who appears calm on the surface. This stress triggers the release of catecholamines, stress hormones that cause blood vessels to dilate. As blood flow increases to certain facial areas, particularly the nose, the temperature rises. Researchers at the University of Granada in Spain documented this effect using thermographic imaging. They found that when people lie, the temperature of the tip of the nose drops slightly first, then increases, while the forehead temperature rises. The overall effect is a warmer nose, detectable with thermal cameras even when invisible to the naked eye. But here's where it gets interesting. The temperature change isn't just from stress alone. It's specifically associated with the cognitive load of lying. Lying requires more mental effort than telling the truth. You have to suppress the true information, construct a false narrative, keep track of what you've said, and monitor the other person's reaction to maintain believability. This mental work generates activity in the prefrontal cortex, and that activity correlates with changes in facial temperature. As for the nose actually growing, the effect is real but microscopic. The increased blood flow causes slight tissue expansion, not visible to the eye but measurable with precise instruments. It's not the cartoonish extension of Pinocchio's wooden nose, but the underlying principle, lying causes physical changes in the nose, holds up. The phenomenon connects to a broader understanding of how emotion and physiology intertwine. When you experience psychological stress, your body responds in specific, predictable ways. The nervous system doesn't distinguish between physical threats and social threats like getting caught in a lie. Both trigger the fight-or-flight response, just at different intensities. Interestingly, the Pinocchio effect is harder to control than other lying indicators. Most people can learn to maintain eye contact while lying, control their hand movements, or keep their voice steady. But you can't consciously control your nose temperature. It's regulated by the autonomic nervous system, the part that operates below conscious awareness. This has obvious implications for lie detection. Traditional polygraph tests measure heart rate, blood pressure, respiration, and skin conductivity. Thermal imaging adds another layer, potentially more difficult to fake. Some researchers have proposed using infrared cameras as lie detection tools, monitoring facial temperature changes during questioning. However, there are limitations. Not everyone shows the same degree of temperature change. Some people, particularly those with certain personality traits or extensive practice lying, might show reduced physiological responses. Stress from being questioned can also cause temperature changes regardless of truthfulness, creating false positives. The effect also reveals something about the nature of deception itself. Lying isn't just a mental act, it's a full-body experience. Your brain might craft the lie, but your cardiovascular system, your endocrine system, even your facial blood vessels participate in the performance. And they don't always cooperate. There's also a psychological dimension worth exploring. The awareness that your body betrays you, even in tiny, invisible ways, adds another layer of stress to lying. It's not just about whether the other person believes you. It's about your own body refusing to fully commit to the deception, creating a physiological dissent that registers even when your words are perfectly controlled. Cultural factors play a role too. In some cultures, lying to maintain social harmony or protect others' feelings is more accepted, and people in those cultures might experience less stress when lying in certain contexts. This could theoretically affect the magnitude of the Pinocchio effect, though research in this area is still limited. The Pinocchio effect is a reminder that we're not as separate from our bodies as we sometimes imagine. Your conscious mind might decide to lie, craft the words, deliver them convincingly. But your body has its own responses, its own tells, its own version of honesty that operates whether you want it to or not. Next time you're tempted to lie, remember, somewhere beneath your conscious control, your nose is warming up, your blood vessels are dilating, and your body is quietly registering the tension between what you're saying and what you know to be true. Pinocchio's growing nose was fantasy, but the principle behind it, that lying leaves physical traces, is grounded in biological reality. Close your eyes right now. Go ahead, actually do it. What do you see? If you're like most people, your first answer might be nothing or blackness. But look closer, or rather experience more carefully. That darkness isn't pure black. It's not the absolute absence of light. It's a specific shade, a dark gray with a slightly luminous quality. That color has a name, Eigengrau. Eigengrau is the German term for intrinsic gray or own gray, and it describes the uniform dark gray that people perceive in the absence of light. It's not true black, which would theoretically be the complete absence of visual stimulation. Instead, Eigengrau is what your visual system produces when there's no external light input. It's the color of your visual neurons at rest, still firing, but without external information to process. The shade is consistent across individuals. Researchers have identified it as roughly equivalent to a dark gray with RGB values around 22, 22, 22 on a 0 to 55 scale, where pure black would be 0, 0, 0. That means Eigengrau is approximately 8–10% lighter than absolute black. It's the default background of your visual experience. But why does your brain produce this particular shade instead of pure blackness? The answer lies in how your visual system functions. Your retina contains photoreceptor cells, rods and cones, that convert light into electrical signals. Even in complete darkness, these cells don't go completely silent. They maintain a baseline level of activity, a sort of neural static. This baseline activity is called neural noise, and it's actually essential for proper visual function. If your photoreceptors were completely inactive in the dark, they'd take longer to respond when light appeared. By maintaining this low level of activity, your visual system stays ready, primed to detect even faint light sources quickly. Eigengrau is the perceptual result of this neural noise. Your brain interprets these baseline signals as a dim, uniform gray rather than as nothing at all. In a sense, Eigengrau is the color of your own neural activity, the visual representation of your visual system idling. The phenomenon becomes more noticeable in complete darkness. In everyday situations, even when your eyes are closed, some light penetrates your eyelids. That faint red glow you sometimes see comes from blood vessels and tissue scattering light. But in truly dark environments, a cave, a dark room, anywhere light is completely absent, Eigengrau emerges more clearly. Interestingly, Eigengrau isn't static. If you pay attention while your eyes are closed in a dark room, you might notice subtle variations, slight patterns or textures moving through the gray. These are called phosphenes, spontaneous perceptions of light that result from mechanical or electrical stimulation of the retina or visual cortex, not from actual light. Eigengrau also changes slightly based on your state. When you're tired, the shade might appear darker. After staring at a bright light, it might seem lighter or take on color tints as your photoreceptors recover. These variations reflect the dynamic nature of your visual system, constantly adjusting and recalibrating. The concept has philosophical implications too. It challenges the intuitive notion that darkness is simply the absence of light, and therefore the absence of visual experience. Instead, Eigengrau suggests that vision is an active process, not a passive one. Your brain doesn't just receive visual information. It constantly generates visual experience, even when there's nothing external to see. This connects to broader questions about perception and consciousness. If your visual system produces Eigengrau in the absence of input, what does that say about the nature of visual experience? It suggests that what you see is always a construction, a product of neural activity, whether that activity is responding to external light or just maintaining its baseline hum. Artists and designers have long understood intuitively that pure black is rare and often unpleasant in visual compositions. The blacks they use are actually very dark grays, closer to Eigengrau than to absolute black. This might be because Eigengrau is more familiar, more comfortable to the human visual system. It's the darkness we know intimately, the one we see every night before sleep. There's also practical relevance in fields like display technology and virtual reality. Understanding that human perception of darkness isn't pure black helps engineers design more natural-looking screens and environments. The goal isn't to reproduce absolute black, but to match the Eigengrau that people naturally perceive. Eigengrau is one of those phenomena that, once you know about it, you can't help but notice. The next time you close your eyes in darkness, you'll recognize it, that specific gray, slightly luminous, slightly textured. It's not nothing. It's the color of your visual neurons at work, the shade your brain paints across your consciousness when the external world goes dark. It's the intrinsic color of seeing itself. You're driving home, a route you've taken hundreds of times. You know every turn, every landmark, but suddenly, mid-drive, nothing looks right. The streets seem unfamiliar. Your own neighborhood feels foreign, like you've never been there before. You know intellectually that you're on the right path, but the feeling of recognition is completely absent. This disorienting experience is called Jamais Vu. Jamais Vu is French for never seen, and it's the opposite of déjà vu. Where déjà vu makes new experiences feel familiar, Jamais Vu makes familiar things feel strange and new. It's a recognition failure, a temporary disconnect between what you know and what you feel. Your memory tells you this is familiar, but your subjective experience says otherwise. The phenomenon can affect anything familiar. A word you've used thousands of times suddenly looks wrong when you write it. Your own face in the mirror seems unfamiliar. A close friend's voice sounds strange. Even your own thoughts or handwriting can trigger the feeling that something you know intimately has become alien. Jamais vu happens because of how recognition works. When you encounter something familiar, your brain doesn't fully process all the details. Instead, it pattern matches, quickly comparing what you're seeing to stored representations. When there's a match, you get that feeling of familiarity, the subjective sense of "I know this." But when that matching process fails or is delayed, even though the memory exists, you experience jamais vu. One common trigger is repetition, similar to semantic satiation. If you repeat a word over and over or stare at your signature until it stops looking like yours, you can induce jamais vu. The neural pathways responsible for recognition become temporarily fatigued, and the familiar becomes strange. stress and fatigue make Jamais Vu more likely. When you're exhausted or anxious, cognitive processes don't function as smoothly. The recognition system might lag or misfire, creating gaps where familiarity should exist. This is why Jamais Vu is more common when you're sleep-deprived or under significant stress. There's also a connection to temporal lobe function, the brain regions involved in memory retrieval and recognition, particularly in the temporal lobes, sometimes show reduced activity or coordination during Jamais Vu experiences. Brain imaging studies have found that when people experience Jamais Vu, there's a disconnect between the areas that process sensory information and those that generate the feeling of familiarity. For most people, Jamais Vu is brief and harmless, lasting seconds to minutes. You might feel momentarily confused or disoriented, but then recognition snaps back into place and everything feels normal again. It's strange and sometimes unsettling, but it passes. However, in some neurological conditions, Jamais Vu can be more frequent or severe. People with epilepsy, particularly temporal lobe epilepsy, sometimes experience it before or after seizures. It can also occur in certain types of migraines, in severe anxiety disorders, or following traumatic brain injuries. In these cases, the frequency and intensity might be significant enough to interfere with daily life. Interestingly, Jamais Vu can sometimes be useful. Researchers have studied it as a way to break mental sets, those rigid patterns of thinking that can block creativity or problem-solving. By making the familiar strange, Jamais Vu forces your brain to re-examine something it normally processes automatically. This fresh perspective can lead to insights or solutions that wouldn't emerge from routine recognition. The phenomenon also highlights something important about identity and selfhood. If your own handwriting, face, or voice can suddenly feel unfamiliar, what does that say about your sense of self? It suggests that even self-recognition is a constructed process, not an inherent quality. You are familiar to yourself because your brain continuously generates that familiarity, not because familiarity is automatically built into being you. Philosophers have explored Jamais Vu as evidence that perception and reality are more separate than we typically assume. The physical reality, the route home, the word on the page, your face in the mirror, hasn't changed, but your experience of it has transformed completely. This demonstrates that subjective experience isn't simply a transparent window onto reality. It's mediated by complex neural processes that can shift and alter what you feel, independent of what's actually there. There's something existentially unsettling about Jamais Vu. It reveals how much of your sense of reality depends on your brain's background processes working correctly. When those processes glitch, even briefly, the ground beneath your experience becomes unstable. The familiar can become foreign in an instant, reminding you that the feeling of knowing and being at home in the world isn't guaranteed. It's actively maintained, continuously, by a brain that sometimes needs a reset. Jamais Vu is a reminder that familiarity is an achievement, not a given. Every moment that the world feels known and recognizable represents your brain successfully matching current experience with stored information. Most of the time, this happens seamlessly, but occasionally the system stutters, and for a disorienting moment, you find yourself a stranger in your own life. Eigengrau also changes slightly based on your state. When you're tired, the shade might appear darker. After staring at a bright light, it might seem lighter or take on color tints as your photoreceptors recover. These variations reflect the dynamic nature of your visual system, constantly adjusting and recalibrating. The concept has philosophical implications too. It challenges the intuitive notion that darkness is simply the absence of light, and therefore the absence of visual experience. Instead, Eigengrau suggests that vision is an active process, not a passive one. Your brain doesn't just receive visual information. It constantly generates visual experience, even when there's nothing external to see. This connects to broader questions about perception and consciousness. If your visual system produces Eigengrau in the absence of input, what does that say about the nature of visual experience? It suggests that what you see, is always a construction, a product of neural activity, whether that activity is responding to external light or just maintaining its baseline hum. Artists and designers have long understood intuitively that pure black is rare and often unpleasant in visual compositions. The blacks they use are actually very dark grays, closer to Eigengrau than to absolute black. This might be because Eigengrau is more familiar, more comfortable to the human visual system. It's the darkness we know intimately, the one we see every night before sleep. There's also practical relevance in fields like display technology and virtual reality. Understanding that human perception of darkness isn't pure black helps engineers design more natural-looking screens and environments. The goal isn't to reproduce absolute black, but to match the Eigengrau that people naturally perceive. Eigengrau is one of those phenomena that, once you know about it, you can't help but notice. The next time you close your eyes in darkness, you'll recognize it, that specific gray, slightly luminous, slightly textured. It's not nothing. It's the color of your visual neurons at work, the shade your brain paints across your consciousness when the external world goes dark. It's the intrinsic color of seeing itself. Jamais Vu. You're driving home, a route you've taken hundreds of times. You know every turn, every landmark. But suddenly, mid-drive, nothing looks right. The streets seem unfamiliar. Your own neighborhood feels foreign, like you've never been there before. You know intellectually that you're on the right path, but the feeling of recognition is completely absent. This disorienting experience is called Jamais Vu. Jamais Vu is French for never seen, and it's the opposite of déjà vu. Where déjà vu makes new experiences feel familiar, Jamais Vu makes familiar things feel strange and new. It's a recognition failure, a temporary disconnect between what you know and what you feel. Your memory tells you this is familiar, but your subjective experience says otherwise. The phenomenon can affect anything familiar. A word you've used thousands of times suddenly looks wrong when you write it. Your own face in the mirror seems unfamiliar. A close friend's voice sounds strange. Even your own thoughts or handwriting can trigger the feeling that something you know intimately has become alien. Jamais vu happens because of how recognition works. When you encounter something familiar, your brain doesn't fully process all the details. Instead, it pattern matches, quickly comparing what you're seeing to stored representations. When there's a match, you get that feeling of familiarity, the subjective sense of "I know this." But when that matching process fails or is delayed, even though the memory exists, you experience Jamais Vu. One common trigger is repetition, similar to semantic satiation. If you repeat a word over and over or stare at your signature until it stops looking like yours, you can induce Jamais Vu. The neural pathways responsible for recognition become temporarily fatigued, and the familiar becomes strange. Stress and fatigue make Jamais Vu more likely. When you're exhausted or anxious, cognitive processes don't function as smoothly. The recognition system might lag or misfire, creating gaps where familiarity should exist. This is why Jamais Vu is more common when you're sleep-deprived or under significant stress. There's also a connection to temporal lobe function. The brain regions involved in memory retrieval and recognition, particularly in the temporal lobes, sometimes show reduced activity or coordination during Jamais Vu experiences. Brain imaging studies have found that when people experience Jamais Vu, there's a disconnect between the areas that process sensory information and those that generate the feeling of familiarity. For most people, Jamais Vu is brief and harmless, lasting seconds to minutes. You might feel momentarily confused or disoriented, but then recognition snaps back into place and everything feels normal again. It's strange and sometimes unsettling, but it passes. However, in some neurological conditions, Jamais Vu can be more frequent or severe. People with epilepsy, particularly temporal lobe epilepsy, sometimes experience it before or after seizures. It can also occur in certain types of migraines, in severe anxiety disorders, or following traumatic brain injuries. In these cases, the frequency and intensity might be significant enough to interfere with daily life. Interestingly, Jamais Vu can sometimes be useful. Researchers have studied it as a way to break mental sets, those rigid patterns of thinking that can block creativity or problem-solving. By making the familiar strange, Jamais Vu forces your brain to re-examine something it normally processes automatically. This fresh perspective can lead to insights or solutions that wouldn't emerge from routine recognition. The phenomenon also highlights something important about identity and selfhood. If your own handwriting, face, or voice can suddenly feel unfamiliar, what does that say about your sense of self? It suggests that even self-recognition is a constructed process, not an inherent quality. You are familiar to yourself because your brain continuously generates that familiarity, not because familiarity is automatically built into being you. Philosophers have explored Jamais Vu as evidence that perception and reality are more separate than we typically assume. The physical reality, the route home, the word on the page, your face in the mirror, hasn't changed, but your experience of it has transformed completely. This demonstrates that subjective experience isn't simply a transparent window onto reality. It's mediated by complex neural processes that can shift and alter what you feel, independent of what's actually there. There's something existentially unsettling about Jamais Vu. It reveals how much of your sense of reality depends on your brain's background processes working correctly. When those processes glitch, even briefly, the ground beneath your experience becomes unstable. The familiar can become foreign in an instant, reminding you that the feeling of knowing and being at home in the world isn't guaranteed. It's actively maintained, continuously, by a brain that sometimes needs a reset. Jamais Vu is a reminder that familiarity is an achievement, not a given. Every moment that the world feels known and recognizable represents your brain successfully matching current experience with stored information. Most of the time, this happens seamlessly, but occasionally the system stutters, and for a disorienting moment, you find yourself a stranger in your own life. The Overview Effect. Imagine floating in orbit, looking down at Earth through the window of a spacecraft. The planet hangs in the darkness, blue and white and alive against the black void. No borders are visible, no signs of conflict or division, just one fragile sphere, rotating slowly, home to everyone and everything you've ever known. Astronauts who have this experience often describe it as transformative, life-changing in ways they struggle to put into words. This phenomenon is called the Overview Effect. The Overview Effect is a cognitive shift in awareness reported by astronauts when viewing Earth from space. It's characterized by a sense of awe, a feeling of unity with all humanity, and a deep understanding of Earth's fragility. Political, national, and racial divisions that seem so important on the ground dissolve from orbit. What remains is the recognition that we're all on the same small planet together. The term was coined by space philosopher Frank White in his 1987 book, The Overview Effect: Space Exploration and Human Evolution. White interviewed numerous astronauts and found remarkably consistent descriptions of how seeing Earth from space altered their perspective. They talked about feeling connected to all life, experiencing a kind of spiritual awakening, and returning with a renewed sense of purpose centered on protecting the planet. Astronaut Edgar Mitchell, who walked on the moon during Apollo 14, described it as an explosion of awareness, a sense that everything is interconnected. Russell Schweickart from Apollo 9 talked about the absurdity of political boundaries from orbit, how arbitrary and meaningless they seemed when viewed from space. These weren't casual observations. For many astronauts, the overview effect was the most profound experience of their lives. What causes this shift? Part of it is purely visual. From orbit, Earth appears small, finite, and isolated in the vastness of space. The atmosphere, which sustains all life, looks paper-thin, a fragile blue shell that could be damaged or destroyed. This visceral understanding of Earth's vulnerability creates an immediate emotional response. But there's also a psychological component. Being in space removes you from the everyday concerns that normally occupy your attention. You're physically separated from national boundaries, cultural conflicts, and individual problems. This distance provides perspective in the literal sense, allowing you to see the bigger picture without the usual filters. Neuroscientists have studied similar experiences of awe and transcendence in other contexts. Brain imaging shows that moments of profound awe activate the default mode network differently than normal experience. The sense of self becomes less rigid, boundaries between self and other blur, and people report feeling connected to something larger than themselves. The overview effect appears to be an extreme version of this response, triggered by the extraordinary experience of viewing Earth from space. The effect isn't limited to professional astronauts. As space tourism develops, civilians who have been to space report similar experiences. They return talking about environmental concerns, human unity, and the need to protect Earth in ways that echo the astronauts' descriptions from decades ago. This consistency suggests the overview effect is rooted in human psychology, not individual personality or training. There's an interesting paradox here. Space exploration, a venture often associated with technological progress and human achievement, consistently produces a deeply humanistic response. Astronauts don't return talking primarily about technology or conquest. They return talking about connection, fragility, and the need for cooperation. The journey outward creates an inward shift. Some researchers believe the overview effect represents an evolutionary response. Humans evolved in specific environments, and our brains are adapted to certain scales and perspectives. Seeing Earth as a whole might activate ancient pattern recognition systems in unexpected ways, creating a sense of home and belonging at a planetary scale that normally operates at the level of immediate surroundings. The implications extend beyond individual experiences. If viewing Earth from space consistently produces feelings of unity and concern for the planet, this raises questions about how to reproduce similar effects for people who will never leave the ground. Can virtual reality recreate the overview effect? Can photographs and video convey it? Some experiments suggest partial success, but nothing seems to match the power of actually being there. The overview effect also challenges certain assumptions about human nature. If our tribal instincts, our tendency toward in-group versus out-group thinking, can be temporarily overridden by a change in perspective, what does that say about the malleability of identity and allegiance? It suggests that under the right conditions, people can expand their circle of concern to encompass all humanity, or even all life on Earth. Philosopher Immanuel Kant talked about the sublime, experiences so vast and overwhelming they exceed our ability to comprehend them fully. The overview effect seems to be a modern example of the sublime, a moment when the scale and beauty of what you're witnessing breaks through normal patterns of thought and feeling, leaving something changed in its wake. Many astronauts describe the experience as spiritual, even if they weren't religious before. It's not necessarily about God or traditional religion. It's about encountering something that feels sacred, meaningful beyond words, and permanently significant. They often struggle to communicate it, saying that no photograph or description fully captures what it's like to actually be there, looking down at the only home humanity has ever known. The overview effect is a reminder that perspective matters, sometimes literally. The same planet that contains endless conflict and division also appears, from the right distance, as a unified whole. The question it poses is whether we need to leave Earth to grasp this truth, or whether we can learn to carry that perspective with us, here on the ground, as we navigate the challenges of sharing this fragile, beautiful world. It starts innocently enough. You hear a song on the radio, maybe just a few seconds of it. Later, hours later, it's back, playing in your mind on repeat. You can't shake it. The melody loops endlessly, sometimes for hours, sometimes for days. You find yourself humming it, tapping it out, unable to think about anything else without the song intruding. This is involuntary musical imagery, more commonly known as an earworm, and it's one of the most common and frustrating quirks of human cognition. Involuntary musical imagery refers to music that plays in your mind without conscious effort or control. It's not that you're choosing to think about the song. It's that the song is thinking itself, using your brain's resources to replay over and over. Nearly everyone experiences this, with studies showing that over 90% of people have at least one earworm per week. The songs that get stuck tend to have specific characteristics. They're usually simple, repetitive, and catchy. Pop songs are frequent culprits, especially choruses with strong hooks. Songs with lyrics that repeat or melodies that don't quite resolve create a kind of cognitive itch. Your brain wants closure, completion, and when a song loops back on itself, it keeps trying to finish what feels unfinished. This connects to something called the Zeigarnik Effect, a psychological phenomenon where incomplete tasks are remembered better than completed ones. Your brain treats an earworm like an unfinished task. The song started, but it didn't properly end, and your mind keeps returning to it, trying to bring it to resolution. The problem is, most earworms don't have clear endings. They just loop, creating a cycle your brain can't escape. But why music specifically? Why don't other things, visual images or spoken phrases, get stuck the same way? Part of the answer lies in how music is processed. Musical memory involves multiple brain regions: auditory cortex for sound, motor cortex for rhythm and movement, emotional centers for feeling, and memory systems for recall. This distributed network means music gets encoded deeply and accessed easily. Music also has a rhythmic structure that aligns with natural brain rhythms. Your brain processes information in cycles, and musical rhythm can sync with these cycles. Once a song locks into your brain's rhythm, it becomes self-sustaining, playing on the existing infrastructure without needing new input. Earworms are more likely to occur when your mind is wandering or when you're doing routine tasks that don't require full attention. Your brain has spare cognitive capacity, and in the absence of external stimulation, it fills the gap with whatever's recently accessible. If you heard a song recently, it's primed and ready to loop. Stress and fatigue make earworms more persistent. When you're tired, your cognitive control weakens. You have less ability to redirect your attention away from the repeating song. Similarly, when you're anxious, your mind tends to loop on things, and an earworm is just another form of repetitive thought. Trying to suppress an earworm often backfires, similar to the classic, "don't think about a white bear" problem. The act of trying not to think about the song actually reinforces it, bringing it back into focus. The more you fight it, the stickier it becomes. So what actually works? Research suggests several strategies. One is to engage with the song fully. Play it through from beginning to end, including the ending. This can satisfy your brain's need for completion and release the loop. Another strategy is to replace the earworm with a different song, ideally one that's less sticky or has a proper ending. Some people call this currying an earworm with another song. Active distraction also helps. Engaging in a task that requires moderate cognitive effort, like reading or conversation, can displace the earworm by filling the mental space it was occupying. Interestingly, chewing gum has been shown to reduce earworms, possibly because it interferes with subvocalization, the subtle movements your vocal cords make when you're imagining sounds. Some researchers suggest that earworms might serve a function. They could be a way your brain keeps musical memories active and accessible. Musicians report more frequent earworms than non-musicians, possibly because their brains are constantly maintaining musical information. The earworm might be a byproduct of memory consolidation, your brain rehearsing and strengthening musical memories. There's also an emotional dimension. Songs that become earworms often have emotional significance. They might be associated with particular memories, moods, or periods of your life. The song isn't just playing because it's catchy. It's playing because it's meaningful, and your brain is drawn back to that meaning repeatedly. Involuntary musical imagery reveals how little control we have over our own thoughts. You can't simply decide to stop thinking about a song. Your brain has its own agenda, its own patterns, and sometimes those patterns lock into loops that feel almost impossible to break. It's a humbling reminder that consciousness isn't a clean, orderly process. It's messy, repetitive, and sometimes stuck playing the same 3 lines of a pop song for hours on end. The next time you have an earworm, instead of fighting it, try observing it. Notice how it loops, where it starts and stops, how your brain fills in missing parts. It's a glimpse into your mind's musical machinery, usually hidden but occasionally making itself known through these persistent, often maddening, sonic loops. You've been playing Tetris for hours. The blocks keep falling, rotating, slotting into place. Finally, you stop and close your eyes, ready for sleep. But the blocks are still there, falling down the inside of your eyelids, rotating, demanding to be arranged. You open your eyes and look at your bookshelf, and suddenly you're mentally rearranging the books into Tetris patterns. You see the skyline outside your window as a series of blocks waiting to be cleared. This is the Tetris effect, and it's not limited to Tetris. The Tetris effect is a phenomenon where engaging intensely with a repetitive pattern-based activity causes you to see those patterns everywhere, even when you're no longer playing. It affects your perception of the real world, your thoughts during the day, and your dreams at night. The activity essentially reprograms your pattern recognition systems, temporarily hijacking them to filter everything through the lens of whatever you've been doing repeatedly. The term comes from a 1994 study where researchers had people play Tetris for extended periods. Players reported seeing Tetris blocks falling when they closed their eyes, arranging objects in their environment into Tetris patterns, and dreaming about the game. What's remarkable is that even people with amnesia, who couldn't remember playing the game, still experienced the visual intrusions. The patterns had embedded themselves at a level deeper than conscious memory. But the effect extends far beyond Tetris. Chess players see knight moves and checkmate patterns everywhere. Gamers who play puzzle games start solving real-world problems using the game's logic. People who spend hours on assembly lines or doing repetitive physical work report seeing the movements and patterns in their mind's eye during breaks and sleep. Medical students studying anatomy see muscles and organs in everyday objects. The effect adapts to whatever pattern your brain has been processing intensively. What's happening neurologically? When you repeat an activity, especially one involving visual patterns and spatial reasoning, you're strengthening specific neural pathways. The more you practice, the more efficient these pathways become. Eventually, they become so active, so well established that they fire spontaneously, even without the original stimulus. Your brain has been trained to look for these patterns, and once trained, it keeps looking whether you want it to or not. This connects to neuroplasticity, the brain's ability to reorganize itself by forming new neural connections. Intensive practice doesn't just make you better at an activity. It physically changes your brain structure. The visual cortex, motor cortex, and pattern recognition systems all adapt to accommodate the repeated task. The Tetris effect is evidence of this adaptation becoming so strong it spills over into other areas of experience. The effect is most intense during what's called the hypnagogic state, that transitional period between wakefulness and sleep. As you drift off, your conscious control weakens, and the trained patterns emerge more freely. This is when Tetris players see the most vivid block formations, when chess players see the clearest board positions, when anyone who's been intensely focused on a pattern sees it most vividly. Dreams amplify the effect further. During REM sleep, your brain processes and consolidates memories, and recent, intensely practiced activities get priority. If you've spent 6 hours playing a video game, your brain treats that as important information worth integrating. The result is dreams where the game's logic and patterns dominate, sometimes blending with other dream content in strange ways. Interestingly, the Tetris effect can be useful. It's a form of procedural learning, the type of learning that makes skills automatic. When pianists dream about finger movements, or athletes dream about their sport, they're actually reinforcing those skills during sleep. Studies have shown that people who experience task-related dreams after practice often show improved performance the next day. But there's a downside. The effect can be intrusive and exhausting. When you can't stop seeing patterns everywhere, when your mind won't let go of the activity even when you want to rest, it becomes mentally draining. People who work in high-intensity pattern recognition jobs, like air traffic controllers or radiologists, sometimes report difficulty shutting off their work brain, constantly seeing patterns and potential problems even when off-duty. The intensity of the effect depends on several factors. How long you've been doing the activity matters. More hours means stronger intrusions. How engaging the activity is also plays a role. Tasks that demand full attention create stronger effects than passive activities. And individual differences matter too. Some people are more susceptible to the effect, possibly due to variations in how quickly their brains form and strengthen neural pathways. The Tetris Effect reveals something profound about perception and consciousness. What you experience as objective reality is actually heavily filtered through recently active neural patterns. Your brain doesn't just passively receive information from the world. It actively interprets everything through the lens of whatever patterns it's been trained to recognize. Spend enough time with any pattern, and it becomes part of how you see. There's also a philosophical dimension. If intensive practice can temporarily reshape your perception of reality, making you see falling blocks or chess moves in neutral stimuli, what does that say about the stability of perception generally? It suggests that what you see is always, to some degree, shaped by what you've been looking at. Your experience of the world is never pure or objective. It's always colored by recent experience, by practice patterns, by neural pathways that have been strengthened through repetition. The effect usually fades within a few days after stopping the activity, as the neural pathways that were strengthened begin to normalize. But during that period, you're living in a world partially transformed by whatever you've been intensely focused on, a temporary reality where everything reminds you of blocks falling, or chess pieces moving, or whatever pattern your brain has decided is important enough to see everywhere. You've been sitting in the same position for hours, completely absorbed in work or a movie. When you finally move, something feels wrong. Your arm doesn't quite seem like yours. Your legs feel distant, disconnected. You know intellectually where your limbs are, but the feeling doesn't match. It's like your body has become unfamiliar, slightly alien. This strange sensation is called proprioception drift, and it reveals just how actively your brain has to work to maintain your sense of where your body is in space. Proprioception is your sixth sense, though it rarely gets called that. It's the sense of body position and movement, the awareness that lets you touch your nose with your eyes closed, or know whether your arm is bent or straight without looking. Specialized receptors in your muscles, tendons, and joints constantly send signals to your brain about position, tension, and movement. Your brain integrates this information to create a coherent sense of your body's configuration in space, but proprioception isn't passive. It requires constant updating. Your brain doesn't just receive body position information, it actively predicts and compares. When you move, your brain predicts what sensory feedback should result, then compares that prediction to the actual feedback it receives. This prediction comparison loop is what gives you smooth, coordinated movement and a stable sense of body position. Proprioception drift happens when this system gets disrupted. When you stay still for extended periods, the flow of proprioceptive information decreases. There's less movement, less change, less updating of body position. Your brain's model of where your body is becomes stale, based on outdated information. The prediction system starts to drift because there's not enough new feedback to correct it. The effect is amplified by restricted blood flow. When you sit or lie in one position too long, circulation to certain areas decreases. This affects the proprioceptive receptors themselves, making them less responsive. The signals they send become weaker or distorted. Your brain is working with degraded information, and the body map it maintains becomes less accurate. You might also experience what's called phantom shifting. where your brain's representation of your limb position doesn't match the actual position. You might feel like your arm is in a different place than it really is, or like your leg is bent when it's straight. This mismatch creates that unsettling feeling of disconnection, like your body parts are where they should be, but don't feel like they're truly part of you. Temperature plays a role too. Extremities that get cold become less sensitive, and proprioceptive receptors don't fire as reliably. This is why your hands or feet can feel especially strange after being in one position in cold conditions. The combination of reduced movement, restricted circulation, and cold temperatures creates a perfect storm for proprioception drift. The experience can be deeply unsettling because proprioception is usually invisible. You don't normally notice it working. It's only when it malfunctions that you become aware of how much you depend on this constant background sense of body position. When it drifts, you're confronted with the fact that your sense of having a body, of being embodied, is an active construction, not a given. Interestingly, proprioception drift can be induced deliberately in laboratory settings. The rubber hand illusion is a famous example. Researchers place a rubber hand in front of a participant while hiding their real hand. They then stroke both the rubber hand and the real hand synchronously. After a few minutes, most people start to feel like the rubber hand is their own hand. They experience proprioceptive drift toward the fake hand, their brain incorporating it into their body representation because the visual and tactile feedback align. This demonstrates something important. Your sense of body ownership is flexible, based on integrated sensory information rather than fixed boundaries. Your brain constantly asks, "What counts as me?" and answers based on patterns of sensory input. When those patterns get disrupted or manipulated, your body sense can shift in surprising ways. Proprioception drift has implications for understanding various clinical conditions. People with certain neurological disorders experience chronic proprioceptive disturbances, where their sense of body position is consistently unreliable. This makes movement difficult and can be psychologically distressing. Understanding proprioception drift in healthy people helps researchers develop better treatments for these conditions. There's also relevance for virtual reality and teleoperation. When people control avatars or robots, they sometimes experience proprioceptive drift toward the artificial body. They start to feel like the avatar's movements are their movements, or the robot's position is their position. This effect is being studied to improve the sense of presence and control in virtual environments. The phenomenon connects to broader questions about embodiment and self. If your sense of where your body is can drift, shift, or even incorporate non-body objects under the right conditions, what does that say about the stability of bodily self-awareness? It suggests that the feeling of being a unified body isn't automatic or permanent. It's maintained through continuous sensory integration, and when that integration is disrupted, even temporarily, the feeling of embodiment becomes uncertain. Recovery from proprioception drift is usually quick. Moving around, stretching, getting blood flowing again rapidly updates your brain's body map. Within seconds or minutes, your limbs feel like yours again, properly connected and located. But during that brief window of disconnection, you get a glimpse into how much invisible work your nervous system does to maintain the seamless experience of having and being a body. Next time you stand up after sitting for hours and your legs feel weird, that's proprioception drift. Your brain needs a moment to recalibrate, to update its model of where your body is and what it's doing. It's a reminder that even the most basic aspects of bodily experience, things so fundamental you never think about them, are active achievements of your nervous system, not passive facts about reality. You learn a new word, maybe Baader or apophenia. Within days, you encounter it everywhere. It shows up in articles you're reading, conversations you overhear, videos you watch. It feels impossible, like the universe is deliberately showing you this word now that you know it. But there's a simpler explanation. The word was always there. You just weren't noticing it before. This is the frequency illusion, also known as the Baader-Meinhof phenomenon. The frequency illusion is a cognitive bias where something you've recently learned about suddenly seems to appear everywhere. It's not that the thing has actually become more common. It's that your brain has started noticing it. Once something enters your awareness, your pattern recognition systems flag it as significant, and you start seeing it in places you would have previously ignored. The phenomenon has two components. The first is selective attention. When you learn something new, your brain tags it as noteworthy. This tagging makes you more likely to notice it in future encounters. Before you learned the word apophenia, you might have read past it without registering. Now, every time it appears, it catches your attention like a highlighted word on a page. The second component is confirmation bias. Once you notice the thing appearing frequently, you interpret this as evidence that it really has increased in frequency. Your brain doesn't naturally track baseline rates. You don't remember all the times you didn't encounter the word before learning it. You only notice the encounters after learning it, and this creates the illusion of sudden ubiquity. The name Baader phenomenon comes from an interesting origin story. In 1994, a person posted on an online forum about learning the name of the Baader group, a German terrorist organization. Shortly after, they encountered references to it multiple times. Other forum members reported similar experiences with different topics, and the term stuck as a label for this cognitive pattern. The frequency illusion affects more than just words. You buy a new car, and suddenly that model is everywhere on the road. You develop a health concern, and suddenly everyone seems to be talking about that condition. You learn about a historical figure, and documentaries, podcasts, and articles about them seem to multiply. In each case, the actual frequency hasn't changed. Your attention has. This connects to how the reticular activating system works. This part of your brain acts as a filter, determining what information makes it to conscious awareness and what gets ignored. You're exposed to millions of pieces of information every day. If everything reached conscious awareness, you'd be overwhelmed. The reticular activating system prioritizes based on what's relevant to your current goals, concerns, and recent experiences. When you learn something new, you're essentially telling your brain, this is relevant. The reticular activating system adjusts its filters accordingly. Now, when that thing appears in your environment, it passes through the filter instead of being screened out. The thing was always there, but it was invisible because your brain deemed it irrelevant until you gave it reason to think otherwise. The frequency illusion can have real consequences. It can lead to false conclusions about trends or patterns in the world. If you learn about a rare disease and then hear about several cases, you might conclude it's becoming epidemic when it's actually just confirmation bias. If you learn about a social problem and start noticing examples everywhere, you might think it's worsening when awareness, not incidence, has changed. This bias also affects how we process news and social media. Once you read about a particular issue or controversy, algorithms notice your interest and show you more related content. This creates a feedback loop where both your attention and the actual presentation of information combine to make something seem far more prevalent than it is. You're experiencing both a psychological bias and a technological amplification of that bias. Understanding the frequency illusion doesn't make it go away, but it can help you compensate. When you notice something appearing everywhere, you can ask yourself, has the frequency actually increased, or have I just started noticing? Is there objective data about trends, or am I relying on personal observation? This kind of metacognitive awareness can prevent false conclusions. The phenomenon also has a positive side. It's part of how learning works. When you learn something new, noticing it in various contexts helps you understand it more deeply. Each new encounter provides additional information, different angles, more complete understanding. The frequency illusion, while technically a bias, facilitates learning by making new information more salient. There's something almost magical about the experience, even when you know the explanation. You learn a new concept, and suddenly the world seems to be teaching you more about it, offering examples and applications everywhere you look. It creates a sense that knowledge opens doors, that learning one thing leads naturally to learning more. And in a way, that's true, not because the universe is conspiring to educate you, but because your brain has been activated to notice what was always there. The frequency illusion is a reminder that perception is selective. You're not experiencing reality directly. You're experiencing what your attention allows through, and attention is shaped by recent experience, current concerns, and what you've tagged as important. The world contains infinite patterns and information. What you see depends on what you're looking for, even when you don't realize you're looking. Your alarm goes off. You silence it and sit up. You're awake technically, your eyes are open, but something is fundamentally wrong. Your thoughts are slow, muddy, incoherent. Your body feels heavy, uncoordinated. Simple tasks, making coffee, getting dressed, require enormous effort. You're moving through fog, struggling to remember what you're supposed to be doing. This state can last minutes or, in some cases, hours. It's called sleep inertia, and it's your brain caught in the transition between sleep and wakefulness. Sleep inertia is the period of impaired performance and reduced alertness immediately after waking. It's characterized by grogginess, confusion, slower reaction times, and difficulty with cognitive tasks. During sleep inertia, you're not fully asleep, but you're definitely not fully awake either. You're stuck in between, with parts of your brain still in sleep mode while other parts are trying to come online. Severity and duration vary widely between individuals and situations. For some people, sleep inertia lasts 5 or 10 minutes. For others, especially after deep sleep or sleep deprivation, it can persist for 2 to 4 hours. During this time, performance on cognitive tasks can be significantly impaired, sometimes worse than if you'd gotten no sleep at all. What's happening in your brain? During sleep, especially deep slow-wave sleep, your brain operates very differently than during wakefulness. Certain regions become less active, connectivity between regions changes, and various neurotransmitter systems shift into different modes. Waking up requires revering all of these changes, but they don't reverse instantly. Different brain regions come back online at different rates. The prefrontal cortex, responsible for executive functions like planning, decision-making, and impulse control, is particularly slow to reactivate. This is why you can be awake enough to walk around and perform basic motor tasks, but still unable to think clearly or make good decisions. Your motor systems have woken up, but your higher cognitive functions are still sluggish. Adenosine, a neurochemical that builds up during wakefulness and promotes sleep, plays a role too. During sleep, adenosine levels decrease, but this process takes time. When you first wake up, adenosine levels might still be relatively high, contributing to continued sleepiness even though you're no longer asleep. Body temperature is another factor. Your core body temperature drops during sleep and gradually rises as you wake. Cognitive performance is closely tied to body temperature, and until your temperature normalizes, your brain doesn't function at full capacity. This is part of why morning showers or exercise help. They raise body temperature and speed up the transition to full wakefulness. The stage of sleep you're waking from matters significantly. If you wake up during light sleep or REM, sleep inertia is usually mild and brief. But if you're pulled out of deep slow-wave sleep, the inertia is much worse. This is why naps longer than 30 minutes can leave you feeling terrible. They last long enough to enter deep sleep, and waking from it creates severe grogginess. Sleep inertia has practical and safety implications. People who need to perform critical tasks immediately upon waking, like emergency responders, military personnel, or healthcare workers on call, can be dangerously impaired during sleep inertia. Studies have shown that decision-making and performance during the first few minutes after waking can be as impaired as if the person were intoxicated. There are strategies to reduce sleep inertia. Strategic timing helps, using sleep cycle tracking to wake during lighter sleep stages rather than deep sleep. Light exposure immediately upon waking accelerates the transition. Bright light signals your brain that it's time to be awake. Caffeine can help, though it takes 15–30 minutes to take effect. And physical activity, even just stretching or walking around, speeds up the process by activating motor systems and raising body temperature. Interestingly, Sleep inertia affects not just cognitive performance but also emotional state. People are often more irritable, anxious, or emotionally fragile during sleep inertia. The emotional regulation systems in the prefrontal cortex are offline, leaving more primitive emotional responses less controlled. This is why small frustrations that wouldn't bother you later can feel overwhelming right after waking. The phenomenon also reveals something about consciousness and the sleep-wake boundary. We tend to think of these as binary states. You're either asleep or awake. But sleep inertia shows it's more of a gradual transition, with mixed states where you're partially both. During sleep inertia, you're conscious enough to respond to your environment and perform actions, but not conscious enough for full cognitive function. Some researchers study sleep inertia to understand consciousness more broadly. If you can be awake but have some brain regions still in sleep mode, what does that say about the nature of consciousness? It suggests that consciousness isn't a single unified state, but rather a collection of processes that can be independently activated or deactivated. There's also a connection to disorders of consciousness. People emerging from comas or recovering from brain injuries sometimes show extended periods similar to sleep inertia, where they're partially responsive but not fully conscious. Understanding normal sleep inertia helps researchers understand these clinical states. Sleep inertia is a reminder that waking up is a process, not an event. The transition from sleep to full wakefulness involves multiple physiological systems gradually coming back online, regions of your brain reactivating in sequence, neurotransmitter levels adjusting, body temperature rising. During that transition, you exist in a liminal state, neither fully asleep nor fully awake, caught in the biology of changing consciousness. You glance at a clock and for just a moment the second hand seems to freeze. It hangs there, suspended, as if time itself has paused. Then suddenly, it ticks forward normally. You might have thought the clock was broken or that you caught it at just the right millisecond. But what you actually witnessed was your brain playing tricks on you. This is the stopped clock illusion, and it reveals something fascinating about how your mind constructs your experience of time. The stopped clock illusion happens because of something your brain does constantly without you ever noticing. It lies to you about gaps in your perception. Every time your eyes move from one point to another, a quick motion called a saccade, your vision essentially goes offline for a fraction of a second. Think about it. If you were consciously aware of every time your eyes darted around, your visual experience would be a chaotic blur of motion. So your brain does something clever. It edits out those moments entirely, but here's where it gets interesting. When you first look at a clock, your eyes have just completed a saccade. Your brain knows there was a gap in your perception, a blank spot where you weren't really seeing anything. To smooth over this gap and make your experience feel continuous, your brain backfills time. It essentially takes the first image you see, the clock's second hand in its current position, and projects it backward to cover the missing moment. The result: that first second appears to last longer than it actually does. Scientists have studied this phenomenon extensively, and it's not limited to clocks. The same effect can happen with any changing stimulus you look at after moving your eyes. Digital timers, blinking lights, even someone's mouth while they're speaking. Your brain is constantly working to create a seamless narrative of reality, even when that means stretching or compressing your perception of time. The illusion reveals a fundamental truth about consciousness. You don't experience reality in real time. There's always a delay, a tiny processing gap between what happens in the world and what you consciously perceive. Your brain is essentially running a slight delay, using that time to edit, enhance, and smooth out your experience. It's like watching a live TV broadcast that's actually on a few seconds delay, allowing the network to censor anything inappropriate. Your brain is doing something similar, but instead of censoring, it's filling in gaps and making predictions. What makes the stopped clock illusion particularly mind-bending is that it challenges our intuitive sense that we see the world as it truly is, in the moment it happens. We like to think of our eyes as cameras, passively recording reality, but they're nothing like cameras. They're active instruments, constantly moving, and your brain is constantly interpreting, predicting, and yes, fabricating parts of what you see to create a coherent experience. The phenomenon also connects to a broader understanding of how your brain handles time perception. Time isn't something you measure objectively in your mind. It's constructed, pieced together from memory, attention, and expectation. When you're bored, time crawls because your brain isn't encoding many new memories. When you're engaged or frightened, time seems to speed up or slow down based on how much information your brain is processing. The stopped clock illusion is just one small example of this construction in action. In practical terms, this illusion is harmless. It lasts only a moment, and you quickly adjust. But it's a window into something profound. The reality you experience is not reality itself, but a carefully crafted simulation your brain presents to you. Every moment of consciousness is your brain's best guess about what's happening, smoothed out, filled in, and presented as seamless experience. The stopped clock doesn't really freeze. Your brain just made you think it did, covering its tracks as your eyes moved. And it does this thousands of times a day without you ever noticing. You're walking down the street and suddenly you see a face staring back at you. But it's not a person, it's a car. The headlights are eyes, the grille is a mouth, and somehow it has an expression. Maybe it looks surprised or angry or even friendly. You know it's just metal and plastic, but you can't help seeing it as a face. This isn't just your imagination running wild. It's pareidolia, a fundamental quirk of human perception that reveals just how obsessed your brain is with faces. Pareidolia is the tendency to perceive meaningful patterns, especially faces, in random or ambiguous stimuli. It's why you see a man in the moon, why clouds sometimes look like animals, why that electrical outlet on the wall seems to be staring at you with a shocked expression. Your brain is so finely tuned to detect faces that it sees them everywhere, even where they don't exist. This behavior isn't a glitch. It's actually a feature, one that's been hardwired into human cognition through millions of years of evolution. For our ancestors, being able to quickly recognize faces was a matter of survival. Spotting a human face in the distance could mean identifying a friend or foe, reading someone's emotional state, or detecting a threat hiding in the environment. The cost of missing a real face was high. You might not recognize danger until it was too late. So the brain evolved to be hypersensitive, erring on the side of caution. Better to see a face that isn't there than to miss one that is. This sensitivity is present from birth. Newborn Bobbies, just hours old, show a preference for looking at face-like patterns over other visual stimuli. 3 dots arranged in a triangle, 2 for eyes and 1 for a mouth, is enough to capture an infant's attention. The brain comes preloaded with a template for what a face should look like, and it applies that template aggressively to the world around it. The neurological basis for pareidolia involves a specific region of the brain called the fusiform face area, or FFA. This area is dedicated almost entirely to processing faces. It's so specialized that damage to it can result in prosopagnosia, or face blindness, a condition where people lose the ability to recognize faces, even those of close family members. But in most people, the FFA is hyperactive, constantly scanning the environment for anything that remotely resembles a face. What's fascinating is that pareidolia isn't limited to visual perception. People sometimes report hearing voices in random noise, like the sound of running water or static. This is the same principle at work. Your brain is searching for patterns, for meaningful information, and when it finds something even vaguely similar to what it's looking for, it locks on. Culturally, pareidolia has inspired countless phenomena. Religious figures seen in toast, tree bark, or water stains often become objects of pilgrimage. The famous Face on Mars, photographed by Viking 1 in 1976, sparked decades of speculation about alien civilizations before higher-resolution images revealed it was just a natural rock formation lit at an unusual angle. But even knowing the truth, people still see the face. The pattern is too strong to ignore. Pareidolia also plays a role in art and design. Emoji, cartoon characters, and even corporate logos often use simplified face-like arrangements because they tap into this deep-seated recognition system. A colon and a parenthesis is enough to convey emotion because your brain interprets it as a face. What makes pareidolia particularly interesting is what it reveals about perception itself. You don't see the world as it is. You see the world as your brain interprets it, filtered through expectations, biases, and evolutionary programming. When you look at a cloud and see a rabbit, you're not discovering something that's objectively there. You're witnessing your brain imposing order on chaos, finding meaning in randomness. It's a reminder that perception is an active process, not a passive reception of information. Your brain is constantly making guesses, filling in gaps, and yes, sometimes seeing faces where none exist. And it does this so automatically, so effortlessly, that you rarely stop to question it. That outlet isn't surprised to see you, but your brain is absolutely convinced it could be. You're at a party and someone pulls out a Ouija board. Hands rest lightly on the planchette and someone asks a question. Slowly, the planchette begins to move, gliding across the board to spell out an answer. No one admits to pushing it. Everyone insists the board is moving on its own. Some believe it's spirits. Others think it's magic. But the real explanation is far more fascinating and reveals something deeply strange about the relationship between your thoughts and your body. This is the Ideomotor Effect, and it's been fooling people for centuries. The Ideomotor Effect refers to unconscious, involuntary muscle movements that occur in response to thoughts, expectations, or mental imagery, without any conscious intention to move. In simple terms, thinking about a movement can cause your body to make tiny, almost imperceptible motions that you're not aware of. These movements are real, they're physical, but they happen entirely outside of your conscious control. The phenomenon was first formally studied in the 19th century, though people have been experiencing it for far longer. Ouija boards, dowsing rods, pendulums used for divination, they all rely on the Ideomotor effect. When someone holds a dowsing rod and walks over ground, they're not consciously moving the rod toward water. But if they expect or hope to find water in a certain spot, their hands make tiny adjustments, subtle tilts and shifts that cause the rod to dip. The person genuinely believes the rod moved on its own, and in a sense it did. Their conscious mind didn't direct the movement, but their unconscious mind absolutely did. What makes the Ideomotor effect so powerful is that the movements are so small and so automatic that they're nearly impossible to detect. When you place your hands on a Ouija board planchette, you're not aware of pushing it, but your muscles are making micro-adjustments, responding to your expectations about what the board might say. If you expect the planchette to move toward yes, your fingers apply just enough pressure, often less than the weight of a coin, to nudge it in that direction. Because multiple people are usually involved, each person's tiny unconscious movements combine, and the planchette glides smoothly, seemingly without anyone pushing. Scientists have tested this repeatedly. When participants are blindfolded and the Ouija board letters are rearranged without their knowledge, the messages become gibberish. The planchette still moves, but it no longer spells coherent words. This proves that the movements are guided by the participants' expectations, not by any external force. Yet even after learning this, people often continue to feel that the board moves on its own. The subjective experience is that powerful. The Ideomotor effect isn't limited to parlor games. It has real-world implications. Facilitated communication, a controversial technique used with nonverbal individuals, has been shown to be driven by the Ideomotor effect. A facilitator holds the person's hand or arm while they type on a keyboard, supposedly helping them communicate. But study after study has shown that the facilitator, not the nonverbal person, is unconsciously guiding the typing. The facilitator genuinely believes the person is communicating, but in reality, they're projecting their own thoughts and expectations through unconscious movements. The effect also appears in more subtle ways. When you're thinking deeply about a direction, left or right, your body might subtly lean that way. If you're imagining lifting your arm, tiny muscle activations occur even if your arm doesn't move. This is why sports psychologists use visualization techniques. Imagining a movement activates some of the same neural pathways as actually performing it, and the Ideomotor Effect produces small, real muscle responses that can enhance performance. What makes the Ideomotor Effect philosophically intriguing is what it reveals about the boundary between conscious intention and unconscious action. We like to think we're in full control of our movements, that nothing happens without our say-so. But the Ideomotor Effect shows that this isn't true. Your mind can move your body without asking permission from your conscious awareness. Thoughts leak into action, expectations shape behavior, and the line between voluntary and involuntary is far blurrier than it seems. The next time you see someone using a Ouija board or dowsing for water, remember, the movement is real, but it's not magic. It's your brain, quietly, invisibly, turning thoughts into motion. The spirits aren't guiding the planchette. You are. You just don't realize it. You're in a car accident. Time slows down. The moment stretches out, every detail sharp and vivid. You see the other vehicle approaching in what feels like slow motion. You have time to think, to react, to notice things you'd normally miss. Then suddenly it's over. The crash happens in an instant, but the memory feels like it lasted much longer. This experience, the sensation that time dilates during high stress or life-threatening events, is called chronostasis. And while it feels like time actually slowed down, what really happened is far stranger. Chronostasis is the illusion that time has slowed or even stopped during a brief, intense moment. It's most commonly reported during accidents, falls, or other Chinese letter situations. But it can also occur in less dramatic contexts, like when you're waiting for something important or caught in an awkward social moment. The key feature is that your subjective experience of time doesn't match the objective passage of time. Seconds feel like minutes. A moment feels stretched. So what's happening in your brain? The answer lies in how memory and attention interact during moments of high arousal. When you're in a dangerous situation, your brain shifts into a kind of emergency mode. Your amygdala, the brain's fear center, becomes highly active, and this triggers a flood of stress hormones like adrenaline and cortisol. These chemicals sharpen your focus and enhance your perception. You become hyper-aware of your surroundings, noticing details you'd normally ignore. Your brain is essentially recording everything at a much higher resolution than usual. Here's where it gets interesting. Time perception isn't something your brain measures directly, like a stopwatch. Instead, your sense of how much time has passed is constructed after the fact, based on the density of memories you've encoded. The more memories you have of a period, the longer that period feels. When you're bored and nothing notable is happening, your brain encodes very few memories, and time seems to fly by. But when you're in a crisis and your brain is recording every tiny detail, the sheer volume of memories makes the event feel like it lasted much longer than it did. This is the heart of chronostasis. Time doesn't actually slow down. Your brain just records the event in much greater detail, and when you recall it later, the richness of those memories tricks you into thinking more time must have passed. It's like the difference between a low-resolution video and a 4K recording. The 4K version contains more information, more frames, and when you play it back, it feels more substantial, even though both videos show the same amount of elapsed time. Researchers have tested this in clever ways. In one experiment, participants were dropped backward into a safety net from a height of 150 feet. During the fall, they were asked to read a rapidly flashing number on their wrist. If time truly slowed down for them, they should have been able to read the number more easily than under normal conditions. But they couldn't. Their perception of time during the event wasn't actually enhanced. However, when asked afterward how long the fall took, participants consistently overestimated the duration. Their memories made the event feel longer, even though their real-time perception was unchanged. This has profound implications. It means that the stretched-out, slow-motion experience people report during accidents isn't happening in the moment. It's a reconstruction, a memory artifact created by the brain's heightened encoding process. You remember the event in slow motion, but you didn't experience it that way in real time. Chronostasis also appears in less extreme situations. The oddball effect is a related phenomenon where an unexpected or novel stimulus in a series of repetitive ones seems to last longer. If you're looking at a sequence of identical images and one different image appears, that odd one out feels like it's on screen longer than the others, even though all images are displayed for the same duration. Again, the brain is encoding more information about the unusual stimulus, and that creates the illusion of extended time. What Chronostasis reveals is that your experience of time is fundamentally subjective and malleable. It's not a fixed, objective measure but a construct your brain builds from attention, memory, and emotion. In moments of fear or surprise, your brain pulls out all the stops, recording everything it can, and that flood of information stretches your sense of duration. Time doesn't slow down. Your brain just convinces you it did. And in the end, when it comes to subjective experience, the distinction hardly matters. If it feels like time stopped, then in your personal reality it did. You're watching someone speak, and you hear them say one thing. But if you close your eyes and listen to the same audio, you hear something completely different. This isn't a trick of the recording or a problem with your hearing. It's the McGurk Effect, one of the most striking demonstrations of how your brain integrates information from multiple senses, and how vision can completely override what your ears are telling you. The McGurk effect was discovered by accident in 1976 by psychologist Harry McGurk and his research assistant John MacDonald. They were studying how children perceive speech, and during their experiments, they noticed something odd. When the audio of someone saying one syllable was paired with video of someone mouthing a different syllable, people didn't hear either one. Instead, they heard a third syllable, a fusion of the two. For example, if the audio says ba, but the video shows someone mouthing ga, most people hear duh. The brain merges the conflicting information into something in between. What makes this effect so powerful is that it's completely involuntary. Even when you know what's happening, even when you're explicitly told that the audio and video don't match, you still experience the illusion. You cannot choose to hear only the audio. Your brain automatically integrates the visual information, and that integration changes your perception. It's one of the clearest examples of how perception isn't just about receiving information from your senses. It's about your brain actively constructing a coherent experience, even when the raw inputs conflict. The McGurk effect reveals something fundamental about how speech perception works. When you listen to someone talk, you're not just using your ears. You're also watching their lips, their facial expressions, and their gestures. All of this visual information gets woven into your understanding of what's being said. In noisy environments, this becomes even more important. Watching someone's mouth move helps you fill in gaps when the audio is unclear. Your brain uses vision to disambiguate sound, to make sense of muffled or distorted speech. Most of the time, this works seamlessly. But when vision and sound give conflicting information, the McGurk effect exposes the process. This phenomenon has been studied extensively in neuroscience. Brain imaging shows that when you're listening to speech, areas of the visual cortex light up, even if you're only hearing the audio. Your brain is anticipating the visual component, preparing to integrate what it sees with what it hears. When both inputs are present, they're processed together in a multisensory area of the brain, where they're combined before you become consciously aware of them. By the time the information reaches your conscious perception, the fusion has already happened. You don't hear audio and see video separately and then combine them. You perceive a unified, already integrated result. The McGurk effect also has practical implications. It's one reason why watching someone speak in person is easier than listening to them on the phone, especially in a noisy environment. The visual cues provide extra information that helps your brain decode the speech. It's also why people who are hard of hearing often benefit from seeing a speaker's face. Lip reading isn't just a backup strategy. It's part of the normal process of understanding speech, even for people with perfect hearing. The effect works across languages, though its strength can vary. It works in children as young as 4 months old, showing that this multisensory integration is a fundamental part of how humans process communication. It even works, to some extent, with computer-generated faces, as long as the lip movements are convincing. What makes the McGurk effect philosophically intriguing is what it says about the nature of reality and perception. You might assume that what you hear is determined entirely by the sound waves entering your ears, but the McGurk effect proves this isn't true. What you hear is influenced, even dominated by what you see. Your senses don't operate independently. They're constantly cross-referencing, checking each other's work, and when they disagree, your brain makes a judgment call about what's most likely to be true. Usually, vision wins. This has a deeper implication. It means that your perception of the world isn't a direct readout of external reality. It's a constructed model, built by your brain from multiple streams of information, weighted and integrated according to rules you're not consciously aware of. The McGurk effect is just one small example, but it points to a larger truth. Everything you see, hear, and feel is your brain's best guess about what's out there. And sometimes, as the McGurk effect shows, that guess is influenced more by what you see than by what's actually being said. You're driving home from a long trip and suddenly you realize you're in your driveway, but you have no memory of the last 20 minutes. You don't remember passing familiar landmarks, making turns, or even stopping at traffic lights. It's as if someone else drove while you were mentally checked out. You might feel a jolt of panic. Did I run a red light? Did I miss my exit? But no, you arrived safely, perfectly on course. This unsettling experience is called highway hypnosis, and it reveals something fascinating about how your brain manages routine tasks. Highway hypnosis, also known as white line fever or driving without attention mode, is a trance-like state that occurs during long, monotonous drives. Your conscious awareness seems to disconnect from the task of driving, yet you continue to operate the vehicle competently, staying in your lane, maintaining speed, and even responding to traffic conditions. It's not sleep. You're awake, but your conscious mind has wandered elsewhere while your unconscious mind handles the driving. This phenomenon happens because of how your brain processes routine, repetitive tasks. When you first learned to drive, every action required intense concentration. You had to think about checking mirrors, adjusting your grip on the wheel, pressing the brake with just the right pressure. But through practice, these actions became automatic. Your brain encoded them into procedural memory, the same type of memory that allows you to tie your shoes or type on a keyboard without thinking about each individual movement. Once a task becomes automatic, your brain no longer needs to devote conscious attention to it. This is actually incredibly efficient. Your conscious mind is a limited resource. It can only focus on so much at once. By automating routine behaviors, your brain frees up conscious awareness for other things like planning, problem-solving, or in the case of highway hypnosis, daydreaming. The problem is that when the environment is monotonous, a long, straight highway with little variation, there's nothing to trigger your conscious attention back to the task. So you drift. The neuroscience behind highway hypnosis involves a shift in which parts of the brain are active. During normal, attentive driving, your prefrontal cortex, the area responsible for executive function and conscious decision-making, is engaged. But during highway hypnosis, activity shifts more toward the basal ganglia, a deeper brain region that handles automatic, learned behaviors. You're still driving, but the driving is being controlled by a different neural system, one that operates below the level of conscious awareness. This state is similar to what happens in other forms of automaticity. When you walk to the kitchen to get something and arrive only to forget what you came for, that's your brain operating on autopilot. When you're reading a book and realize you've processed several paragraphs without actually absorbing any of the content, that's the same phenomenon. Your brain is capable of performing complex tasks without conscious supervision, and it does this more often than you realize. What makes highway hypnosis particularly striking is that driving is a high-stakes activity. The consequences of inattention can be severe, yet people regularly experience these memory gaps and arrive safely. This suggests that the unconscious mind is surprisingly competent at handling routine navigation and motor control. Studies have shown that during highway hypnosis, drivers can still respond to basic traffic demands. If a car ahead brakes suddenly, you'll brake too, even if you later have no memory of doing so. Your brain is still monitoring the environment, but it's doing so at a subconscious level. However, highway hypnosis is not without risks. While your unconscious mind can handle routine situations, it's not as good at responding to unexpected events. If something unusual happens, a child running into the road, an animal darting out, a sudden construction zone, your reaction time may be slower because your conscious attention isn't engaged. This is why highway hypnosis is more dangerous than it might seem. You're driving competently in predictable conditions, but you're less prepared for the unpredictable. The conditions that promote highway hypnosis are well understood. Long, straight roads with minimal visual variation are the primary culprit. Highways through flat terrain, especially at night, are notorious for inducing the state. Fatigue makes it worse, as does monotonous engine noise or the rhythmic sound of tires on pavement. Even being a passenger on a long trip can induce a similar trance-like state, where you zone out and lose track of time. To combat highway hypnosis, drivers are advised to introduce variation. Change your driving position slightly. Adjust the temperature. Listen to engaging music or podcasts. Take regular breaks. Chew gum. Anything that brings your conscious attention back online. The key is to disrupt the monotony that allows your brain to coast on autopilot. What highway hypnosis reveals is both reassuring and unsettling. It's reassuring because it shows that your brain is incredibly efficient, capable of handling complex tasks without conscious effort. But it's unsettling because it highlights how much of your life you might be living on autopilot, going through the motions while your conscious mind is elsewhere. How often do you arrive somewhere with no memory of the journey? How often do you complete tasks without really being present? Highway hypnosis is an extreme example, but it's part of a broader pattern. Your brain is always looking for ways to conserve conscious attention, and when the environment allows it, you drift. The road passes beneath you and you arrive, but in a very real sense, you weren't fully there. You've finished most of your work for the day, checked off nearly every item on your to-do list. But there's one task left, something small and unimportant, and you tell yourself you'll get to it tomorrow. Yet as you try to relax, that unfinished task keeps creeping back into your mind. It nags at you. It occupies mental space far beyond what it deserves. Meanwhile, the 10 things you already completed barely register. This imbalance, where unfinished tasks dominate your thoughts while completed ones fade away, is called the Zeigarnik Effect, and it's one of the mind's strangest quirks. The Zeigarnik Effect was discovered in the 1920s by Russian psychologist Bluma Zeigarnik, who supposedly got the idea from observing waiters in a cafe. She noticed that waiters could remember complex, unpaid orders in great detail, but once an order was paid, they seemed to forget it almost immediately. Intrigued, she designed experiments to test whether unfinished tasks really do occupy more mental space than completed ones. Her findings confirmed it. People remember interrupted or incomplete tasks significantly better than tasks they've finished. The reason for this lies in how your brain manages goals and intentions. When you start a task, your brain creates a kind of mental marker, a cognitive tension that persists until the task is complete. This tension keeps the task active in your working memory, ensuring you don't forget about it. It's like opening a loop that your brain wants to close. As long as the task remains unfinished, that loop stays open and your brain continues to allocate attention to it, even when you're not actively working on it. Once you complete the task, the loop closes. The cognitive tension dissipates. Your brain no longer needs to hold the task in working memory, so it gets filed away or forgotten. This is why finished tasks seem to vanish from your mind. They've served their purpose, but unfinished tasks remain active, demanding attention, creating a persistent background hum of mental pressure. This effect has profound implications for how you experience productivity and stress. That growing to-do list doesn't just represent work you need to do. Each item on it is an open loop, a source of cognitive tension. The more unfinished tasks you have, the more mental bandwidth they consume, even when you're not consciously thinking about them. This is why you might feel mentally exhausted at the end of a day where you didn't accomplish much. It's not just the lack of progress that's draining. It's the accumulation of open loops. The Zeigarnik Effect also helps explain procrastination guilt. When you put off a task, it doesn't leave your mind. It stays there, nagging, creating discomfort. The longer you avoid it, the more mental space it occupies. Paradoxically, the task often feels bigger and more daunting in your mind than it actually is in reality. Starting the task, even making a tiny bit of progress, can provide relief because it reduces that cognitive tension. This is why productivity experts often recommend just starting, even if you only work for 5 minutes. Starting transforms the task from a vague, looming presence into something concrete and manageable. Interestingly, the Zeigarnik Effect doesn't require the task to be important. Even trivial, unfinished tasks can occupy disproportionate mental space. That email you meant to send, that book you started but never finished, that drawer you planned to organize. These small, insignificant items can clutter your mind far more than major accomplishments. Your brain doesn't distinguish based on importance. It only cares whether the loop is open or closed. The effect also shows up in entertainment. Cliffhangers in TV shows exploit the Zeigarnik Effect. When an episode ends on an unresolved moment, your brain wants closure. That open loop keeps the story active in your mind, making you more likely to watch the next episode. Serialized storytelling, from novels to podcasts, uses the same principle. Finishing a chapter or episode provides satisfaction, but starting the next one reopens the loop, pulling you forward. On the flip side, the Zeigarnik Effect can be harnessed productively. If you're working on a large project, intentionally stopping in the middle of a task, rather than at a natural endpoint, can make it easier to resume later. When you stop mid-sentence or mid-thought, the cognitive tension ensures you remember where you were and what you were doing. It's why some writers stop in the middle of a paragraph at the end of a writing session. The unfinished thought pulls them back to the work the next day. But there's a cost to constantly living with open loops. Chronic unfinished business contributes to mental fatigue, anxiety, and a persistent sense of being overwhelmed. This is why completion is so satisfying. Finishing a task doesn't just mean the work is done. It means your brain can finally let go, releasing the cognitive tension that's been simmering in the background. The Zeigarnik Effect reveals that your mind is not neutral about what you remember. It prioritizes unfinished business because, evolutionarily, incomplete goals were often matters of survival. If you started building a shelter and left it unfinished, you needed to remember to go back. If you began tracking an animal and lost the trail, your brain needed to keep that goal active. In modern life, the stakes are lower, but the mechanism remains. Your brain treats every unfinished task as important, whether it is or not. That half-written email, that unmade phone call, that one item left on your list, they sit there, taking up space, demanding attention until you finally close the loop. Only then can your mind move on. You feel your phone buzz in your pocket. You reach for it expecting a text or notification. But when you check, there's nothing. No messages, no alerts. The phone is silent. You're certain you felt it vibrate, but it didn't. You dismiss it as a mistake and go back to what you were doing. Then 10 minutes later, it happens again and again. Welcome to phantom vibration syndrome, a strange modern phenomenon where your brain manufactures sensations that aren't there, all because it's anticipating something that might happen. Phantom vibration syndrome, sometimes called rinxiety or phantom ringing, is the sensation that your phone is vibrating or ringing when it isn't. It's surprisingly common. Studies suggest that anywhere from 70 to 90% of people with smartphones have experienced it at least once. For some, it's an occasional oddity. For others, it happens multiple times a day. And what makes it particularly strange is that the sensation feels completely real. You're not imagining it in the sense of daydreaming. You actually feel a vibration, a tactile sensation on your skin, even though nothing physical caused it. The root of phantom vibration syndrome lies in how your brain processes expectations and sensory information. Your phone has become a constant presence in your life, a source of frequent stimulation. Texts, emails, social media notifications, they arrive unpredictably, creating a pattern of intermittent reinforcement. You never know exactly when the next notification will come, which keeps your brain in a state of anticipation. This is the same mechanism that makes slot machines addictive. The unpredictability keeps you alert, waiting for the next reward. Over time, your brain becomes hypersensitive to signals that might indicate your phone is buzzing. It starts to interpret ambiguous sensory information, like the feeling of fabric shifting against your leg or a muscle twitch, as a phone vibration. This is a form of learned pattern recognition gone into overdrive. Your brain is so primed to detect the vibration that it begins to generate false positives, seeing patterns where none exist. This phenomenon is related to a broader concept called apophenia, the tendency to perceive meaningful connections or patterns in random or ambiguous data. Your brain is a pattern detection machine. It's constantly scanning the environment for signals, and it's biased toward overdetection rather than underdetection. From an evolutionary standpoint, this makes sense. Missing a real signal, like the sound of a predator, could be deadly. Perceiving a false signal, like mistaking wind for danger, is relatively harmless. So your brain errs on the side of caution, detecting patterns even when they're not there. Phantom vibration syndrome is a modern manifestation of this ancient bias. Your phone has become a signal source that your brain monitors constantly, and because missing a notification can feel urgent, your brain has lowered the threshold for detection. It's essentially creating a phantom signal to ensure you don't miss a real one. The sensation is your brain saying, check the phone just in case. Phenomenon is more common in people who are highly attached to their phones or who experience anxiety around missing messages. If you're waiting for an important text or email, your brain becomes even more vigilant and phantom vibrations increase. The anxiety creates a feedback loop. You're anxious about missing something, so your brain becomes hypersensitive, which causes more phantom sensations, which reinforces the habit of constantly checking your phone. Phantom vibration syndrome also has a social component. In cultures where being constantly available is expected, people feel pressure to respond quickly to messages. This pressure heightens the brain's monitoring of the phone, increasing the likelihood of phantom vibrations. In a sense, the syndrome is a byproduct of modern communication norms, where the phone has become an extension of social presence. Interestingly, phantom vibrations usually occur in the same location where you typically carry your phone. If you keep your phone in your right pocket, that's where you'll feel the phantom vibration. If you carry it in a purse or bag, the sensation might occur near your shoulder or hip. This specificity shows that your brain has learned to associate a particular body location with the phone's vibration, and it's that learned association that generates the false sensation. The sensory cortex, the part of your brain that processes touch, can be influenced by expectation. When you're anticipating a sensation, the neurons in the sensory cortex become more excitable, lowering the threshold for activation. This is why you might feel a phantom vibration even from very minor stimuli that wouldn't normally register as touch. Your brain is in a heightened state of readiness, and it interprets ambiguous signals as the expected sensation. Phantom vibration syndrome isn't harmful, but it does reveal something about how technology is reshaping your sensory experience. Your brain has adapted to the presence of the smartphone to such a degree that it now generates sensations in anticipation of its signals. It's a kind of learned hallucination, a false perception created by expectation and habit. Some people find phantom vibrations annoying and try to reduce them by changing notification settings, taking breaks from their phones, or simply becoming more aware of the phenomenon. Awareness itself can help. When you recognize that the sensation is a false alarm generated by your own brain, it becomes easier to dismiss. Others barely notice or care, treating it as a minor quirk of modern life. What phantom vibration syndrome ultimately shows is how malleable your perception is. You don't passively receive sensory information. Your brain actively predicts what it expects to sense, and those predictions can shape what you actually feel. Your phone hasn't buzzed, but your brain is so convinced it might have, so focused on not missing a signal, that it creates the sensation anyway. You feel it. You reach for your phone, and you find nothing. But the phantom vibration has already done its job, keeping you alert, keeping you connected, keeping you checking just in case. You spill coffee on your shirt right before a meeting. As you walk into the room, you're painfully aware of the stain. You're convinced everyone is looking at it, judging you, thinking you're careless or unprofessional. But when you glance around, no one seems to notice. They're focused on their own notes, their phones, their own thoughts. By the end of the meeting, you realize that the thing you were so worried about barely registered with anyone else. This is the spotlight effect, and it's one of the most common cognitive distortions people experience. The spotlight effect is the tendency to overestimate how much other people notice your appearance, behavior, or mistakes. It's the feeling that you're on stage, under a spotlight, with everyone watching your every move. In reality, people are far less focused on you than you think. They're busy dealing with their own concerns, their own insecurities, and their own version of the spotlight effect. This phenomenon was formally studied by psychologists Thomas Gilovich and Kenneth Savitsky in the 1990s. In one famous experiment, they had participants wear embarrassing t-shirts, ones featuring outdated or uncool images, and then enter a room full of other people. Afterward, the t-shirt wearers were asked to estimate how many people in the room noticed their shirt. On average, they guessed about 50%. But when the other people were asked, only about 25% actually remembered seeing the shirt. The participants felt conspicuous, but in reality, they were far less noticeable than they believed. The spotlight effect happens because of a fundamental bias in how you perceive yourself versus others. You are the center of your own experience. You're acutely aware of your appearance, your mistakes, your awkward moments, because you experience them from the inside. But other people don't have that access. They see you externally, as one element in a complex environment full of competing stimuli. Their attention is divided, and unless you do something truly dramatic, you're just part of the background. This bias is amplified by the fact that you spend a lot of time thinking about yourself. You rehearse conversations, replay embarrassing moments, worry about how you're perceived. This constant self-focus makes you feel like you must be equally prominent in other people's minds. But the truth is, other people are doing the same thing. They're focused on their own internal experience, not on scrutinizing yours. The spotlight effect applies to both positive and negative situations. If you give a great presentation, you might think everyone will remember it and talk about it. But most people will forget the details within a day or two. If you make a mistake, you might agonize over it, convinced everyone noticed and is judging you. But chances are, most people either didn't notice or didn't care. Their attention was elsewhere. This effect has real consequences for social anxiety. People with social anxiety often experience an exaggerated version of the spotlight effect. They believe they're under constant scrutiny, that every mistake is magnified, that everyone is forming negative judgments. This belief can make social situations feel unbearable, leading to avoidance and isolation. But the reality is that people are generally far more forgiving and far less attentive than the anxious mind assumes. The spotlight effect also impacts decision-making. Fear of judgment can prevent people from taking risks, speaking up, or expressing themselves. You might stay silent in a meeting because you're worried your idea will sound stupid, even though everyone else is probably too focused on their own thoughts to judge yours harshly. You might avoid trying something new, wearing something bold, or pursuing a goal because you're convinced everyone will notice and criticize. But in most cases, people won't notice, and if they do, they'll forget quickly. Understanding the spotlight effect can be liberating. It means that most of your social fears are based on a distorted perception. The embarrassing thing you did last week, the people who witnessed it have probably already forgotten. The awkward thing you said. It didn't register as strongly with others as it did with you. The outfit you're worried about. Most people won't notice or care. There's a related concept called the illusion of transparency, which is the belief that your internal states, your nervousness, your discomfort, your emotions, are more visible to others than they actually are. When you're anxious, you feel like everyone can see your anxiety. But studies show that people are generally very bad at detecting others' internal states unless they're explicitly shown. Your racing heart, your sweaty palms, your internal panic, these are invisible to others. They see your external behavior, which is usually much calmer than you feel inside. The spotlight effect isn't universal. In some situations, you really are being observed and judged, like during a job interview or a performance. But even in these contexts, people tend to overestimate the intensity and duration of others' attention. And in everyday life, in casual social interactions, the effect is even stronger. Most people are too wrapped up in their own concerns to pay sustained attention to yours. So what does this mean practically? It means you can afford to relax. You can afford to take more risks, to be more authentic, to worry less about small mistakes. The spotlight you feel isn't real. It's a projection of your own self-focus onto others. In reality, people are focused on themselves, dealing with their own spotlights, their own insecurities. You're not on stage. You're just another person in the audience, occasionally glancing around but mostly absorbed in your own experience. The stain on your shirt, the awkward comment, the bad hair day, they matter far less to others than they do to you. And once you internalize that, the imaginary spotlight dims and you're free to just be. You're lying down, staring at a perfectly uniform field of color. Maybe it's a blank white wall, maybe it's half a ping-pong ball placed over each eye while a red light shines through. At first, nothing happens, but after a few minutes, something strange begins. The color seems to shift, to shimmer. You start seeing patterns that aren't there, swirls, shapes, faces. Then full-blown hallucinations. Vivid images, scenes, sometimes even entire landscapes. You're not dreaming, you're wide awake. This is the Ganzfeld Effect, and it happens when your brain is starved of sensory input. The Ganzfeld Effect occurs when you're exposed to an unstructured, uniform field of stimulation. The term comes from the German word Ganzfeld, meaning complete field. In experimental settings, researchers create this by having participants wear eye coverings that diffuse light into a uniform glow, or by placing them in environments with no variation in color or texture. The effect also works with sound. Listening to white noise or continuous, unchanging tones can produce similar results. The key is homogeneity, an environment where there's nothing for your senses to latch onto, no edges, no contrasts, no patterns. Under normal conditions, your sensory systems are constantly processing a stream of varied information. Your eyes scan the environment, picking up shapes, colors, movements. Your brain takes this input and constructs your visual experience. But when the input becomes completely uniform, your visual system has nothing to work with. There's no new information to process, no changes to detect. And this is where things get strange. Your brain doesn't respond to sensory deprivation by shutting down. Instead, it does the opposite. It becomes more active. When external input drops below a certain threshold, your brain starts generating its own signals to fill the void. This is called spontaneous neural activity. In the absence of real sensory data, your visual cortex begins firing on its own, creating patterns, shapes, and images. These aren't voluntary. You're not imagining them in the sense of daydreaming. They appear to you as perceptions, as if they're really there. The hallucinations produced by the Ganzfeld effect can range from simple geometric patterns, dots, lines, grids, to complex fully formed images. Some people report seeing faces, animals, or entire scenes. Others experience shifts in color, where the uniform field seems to change hue even though the physical stimulus remains constant. The content of the hallucinations varies from person to person, but the experience of seeing something that isn't there is nearly universal if the Ganzfeld condition is maintained long enough. This phenomenon reveals a fundamental truth about perception. It's not passive. Your brain isn't just a receiver recording whatever the senses deliver. It's an active interpreter, constantly making predictions and filling in gaps. Under normal conditions, sensory input keeps these predictions grounded in reality. But in a Ganzfeld environment, where there's no input to constrain the brain's activity, the predictions run free. You start perceiving the brain's internal activity, as if it were external reality. The Ganzfeld effect has been studied extensively, both for its own sake and as a tool for exploring consciousness. In the 1930s, psychologist Wolfgang Metzger conducted early experiments by having participants stare at uniformly illuminated screens. He noted that after a few minutes, people reported that the visual field seemed to dissolve, becoming fog-like, and that they began seeing shapes and forms that weren't present in the stimulus. Later, the Ganzfeld technique was used in parapsychology research. Researchers hypothesized that reducing external sensory input might make people more sensitive to subtle, non-ordinary perceptions, like ESP or telepathy. Participants would be placed in a Ganzfeld state and then tested to see if they could receive information through extrasensory means. While these studies remain controversial and have not produced conclusive evidence for psychic phenomena, they did consistently demonstrate that the Ganzfeld state produces altered perceptions and vivid mental imagery. The effect is also related to sensory deprivation experiments conducted in the mid-20th century. Researchers found that when people were isolated in environments with minimal sensory input, dark, soundproof chambers, they often experienced hallucinations, disorientation, and anxiety. The brain, deprived of its usual stream of information, begins to malfunction, or more accurately, it begins to function without constraints. The hallucinations are a side effect of a brain trying to make sense of nothingness. What makes the Ganzfeld effect particularly interesting is that it doesn't require drugs, sleep, or any altered state of consciousness beyond simply staring at uniformity. It shows that your normal waking perception is more fragile than you might think. The line between seeing what's really there and seeing what your brain generates is thinner than it seems. Under the right conditions, your brain will happily show you things that don't exist, and it will present them with the same vividness and apparent reality as genuine perceptions. The Ganzfeld effect also has implications for understanding other hallucinatory experiences. Hallucinations in conditions like schizophrenia, migraines, or sensory loss might involve similar mechanisms. When the brain's predictive processes become unmoored from sensory input, whether because of neural dysfunction or lack of input, hallucinations can result. The Ganzfeld effect is a controlled, temporary version of this process, offering a window into how perception can break down and how the brain fills in the blanks when reality goes quiet. In everyday life, you're unlikely to encounter a true Ganzfeld environment, but milder versions of the effect can happen. Staring at a blank wall for too long, driving through dense fog, or even lying in a completely dark room can produce subtle visual distortions. Your brain, always eager to find patterns, starts creating them when the world doesn't provide enough. The Ganzfeld effect is an extreme demonstration, but it's a reminder of what's always happening behind the scenes. Your perception isn't a mirror of reality. It's a construction, a simulation your brain creates from sensory data. And when that data disappears, the simulation continues anyway, pulling from memory, expectation, and random neural noise. You see things that aren't there because, in a very real sense, your brain never stops creating what you see, whether the world cooperates or not. You're at a party, a busy restaurant, a crowded train station. A wall of sound surrounds you, dozens of conversations, clattering dishes, background music. It's an undifferentiated hum, a single blur of noise to your conscious mind. And then from somewhere across the room, a voice cuts through it all. Not a shout, not a scream, just the sound of your own name. How is that possible? Your ears didn't magically become more sensitive. Your brain simply decided that one specific piece of information, out of the thousands hitting you every second, was critical enough to elevate into your awareness. This is the cocktail party effect, one of the most elegant demonstrations of your mind's selective attention. It's as if your consciousness has a bouncer at the door of your perception, filtering the chaotic sensory guest list, letting only the most important or relevant signals through to the main event of your awareness. All the other sounds are still there. Your brain is still processing them at some level enough to notice a shift in tone or a familiar laugh, but they remain in the auditory background. This ability isn't just about names. It's the parent who hears their child's faint cough over the roar of a television. It's the drowsy listener who tunes into an alarm clock through deep sleep. It reveals a fundamental truth. You are not a passive recorder of reality. You are an active and highly selective editor. Your experience of this moment is not the whole show. It is a carefully curated highlight reel, chosen by a silent editor in the depths of your mind, working tirelessly to tell you what, out of everything happening, you actually need to know. Imagine stepping off a roller coaster, your heart hammering against your ribs, your breath coming in short gasps, your entire body humming with a heightened electric awareness of being alive. Now, imagine meeting someone's eyes in that precise moment. The connection might feel intense, profound, almost destined. But is it the person or is it the precipice? This is the misattribution of arousal, a quirk of human emotion where we mistake the source of our own physiological excitement. Your body has a limited vocabulary for arousal. The same racing heart, sweaty palms, and shortness of breath can signal fear, excitement, anger, or attraction. Your brain, seeking a neat narrative for this internal storm, looks to the environment for a label. If you're on a shaky footbridge, it calls it fear. If you're watching a thrilling game, it calls it excitement. And if you're on a date where you just watched a suspenseful film or walked through a slightly perilous part of town, it can very easily mislabel that borrowed adrenaline as romantic chemistry. This is why a scary movie date can feel so potent, or why intense shared challenges can forge powerful bonds. You are, in a very real sense, borrowing intensity from one experience and lending it to another. The phenomenon asks a quiet, unsettling question about the fabric of our feelings. How much of what we call love, or connection, or even hatred is a pure, unadulterated emotion, and how much is simply our brain's best guess, a story it spins to explain the mysterious weather systems of our own bodies? It suggests our deepest emotions are not always pristine discoveries, but sometimes clever and often flawed interpretations. You remember a scene, a line, a logo, a historical detail with crystal clarity. You can describe it, you can feel the memory. And then you discover with a jolt that it never happened that way. The Monopoly man never had a monocle. The Fruit of the Loom logo never featured a cornucopia. And Nelson Mandela did not die in a South African prison in the 1980s. He was released, became president, and passed away in 2013. Yet for thousands of people, these false memories are not vague. They are vivid and shared. This is the Mandela Effect, the eerie phenomenon where large groups of people independently recall the same specific detail or event incorrectly. The standard explanation is a tapestry of cognitive glitches, our imperfect memories merging with suggestions, pop culture parodies, or common assumptions. Our brains are storytellers, not archivists, and they happily fill in gaps with plausible details, which then solidify into false certainty. But the sheer consistency of these errors, across disparate people with no direct connection, gives the phenomenon its haunting quality. It has, of course, spawned more speculative theories, whispers of glitches in a simulation, or the brushing of parallel timelines where events did unfold differently. Whether you see it as a fascinating bug in our collective cognitive software or a hint of something stranger, the Mandela Effect serves as a profound communal humility check. It demonstrates that memory is not a personal video file, but a fragile, reconstructive act. And when we all reconstruct the same error, it reveals not just how our individual minds work, but how our shared consciousness can, in quiet unison, collectively misremember the world. Close your eyes and point to your left knee. You can do it instantly without looking. This silent, internal map of your body in space is called proprioception, your sixth sense of self. Now, imagine that sense persisting for a part of you that is no longer there. For many amputees, the vivid, undeniable sensation of a missing limb does not vanish. This is the phantom limb. It is not a memory or a metaphor, but a real, often persistent sensory experience. They may feel an itch on a phantom foot, a cramp in a phantom hand, or the specific, ghostly posture of the limb at the moment it was lost. The most poignant and painful version is phantom pain, a burning, twisting, or searing agony emanating from empty space. Modern neuroscience explains this not as a psychological quirk, but as a literal remapping of the brain. The region of the somatosensory cortex that once received signals from that limb falls silent but does not disappear. Like neighboring territories expanding into unclaimed land, the brain areas for the face, torso, or the remaining limb begin to activate these unused neurons. A touch on the cheek might now be felt, bewilderingly, in the phantom hand. The phantom is a testament to the brain's stubborn, persistent model of the body, a model so deeply wired that it resists updating, even in the face of absolute physical evidence to the contrary. The phantom limb is perhaps the most intimate and paradoxical proof that what you feel as your physical self is, in the end, a sophisticated construction, a story written in neural pathways that can, at times, outlast the very flesh it was meant to describe. You learn a new word, say, petrichor, the smell of rain on dry earth. The next day you read it in a novel. 2 days later a podcast host uses it. Suddenly it seems to be everywhere. Or you notice a specific model of car, perhaps an older, distinctive one. Once you see it, you start seeing it on every street, in every parking lot. The world feels suddenly, strangely saturated with it. This is the Baader-Meinhof phenomenon, or the frequency illusion. It feels uncanny, even meaningful, as if the universe is sending you a signal. In reality, it is a perfect storm of two cognitive processes. The first is selective attention. Your brain has a new item on its mental checklist, petrichor, that specific car, and now, like a hypervigilant scout, it highlights that item every time it appears in the endless stream of daily data. The item wasn't rare before, you were simply blind to it. The second process is confirmation bias. You note every confirming instance. There it is again. While effortlessly ignoring the vast background of moments when it didn't appear. The phenomenon is named, with ironic obscurity, after the West German militant group Baader-Meinhof. The story goes that after learning about them, a commenter began seeing references to them everywhere. The name stuck, itself becoming a subject of the very phenomenon it describes. It's a gentle reminder of your mind's active role in shaping your reality. The world is not suddenly filling with new things. Instead, you have given your perception a new filter, and in doing so, you have painted your experience with a different shade of significance. The universe isn't whispering secrets. It's your own awakening attention, listening to itself here. In a quiet room, without a word spoken, the breathing of two close friends can begin to fall into a shared, silent rhythm. In a crowd at a concert, thousands of individual heartbeats don't just respond to the music. They subtly begin to harmonize with each other. This is entrainment, the unconscious, often invisible, synchronization of biological rhythms between living beings. It's the phenomenon where your heartbeat, your breathing rate, even the timing of your gestures, can slowly attune themselves to the people around you. We see it in the precise, flowing unity of a rowing team, where individual exertion becomes a single, pulsing organism. We hear it in the applause of an audience, which within moments coalesces from chaotic noise into a steady, unified clap. On a fundamental level, it's your body's quiet diplomacy, a biological mirroring that fosters connection and cohesion. Scientists believe this synchronization is rooted in our social brain's drive for empathy and prediction. By subtly aligning our internal states with another's, we create a shared physiological platform, making it easier to understand their emotions and intentions. It's a conversation that happens far below language, in the ancient dialects of pulse and breath. This is why being around a frantic, anxious person can leave you feeling unsettled, while time spent with someone profoundly calm can slow your own world down. Entrainment reveals that we are not closed, isolated systems. We are permeable, resonating beings, constantly tuning ourselves, and being tuned by the invisible rhythms of others. Our bodies, in their quiet wisdom, understand unity long before our minds ever put it into words. We spend so much energy crafting an image of competence, of flawlessness. We rehearse presentations, polish our words, and hide our stumbles. But what if the secret to being genuinely liked lies not in perfection, but in a perfectly timed minor imperfection? This is the Pratfall Effect. It's the counterintuitive finding that someone who is already seen as competent or admirable can actually become more likable, more relatable, after committing a small, harmless blunder. Spilling a little coffee during a meeting, fumbling a word in an otherwise eloquent speech, or admitting a trivial, universal human foible. The effect works because the mistake serves two powerful psychological functions. First, it humanizes. It punctures the intimidating bubble of perfection, making you accessible and proving you inhabit the same messy, error-prone world as everyone else. Second, it creates a moment of shared, sympathetic vulnerability in the observer. The audience, instead of judging, often feels a mild, empathetic thrill of, "Oh, I've been there." Their brain subconsciously relaxes. The key, of course, is that the pratfall must follow established competence. A series of major failures doesn't charm, it confirms inadequacy. But a single, small stumble after a display of skill acts as a social signal. It whispers, "I am capable, but I am also real." It's a subtle reminder that we are not seeking flawless machines in our fellow humans. We are seeking connection. And sometimes, the most reliable bridge to another person is not a triumph, but a shared, gentle acknowledgement of the stumble. Stare for a moment at a single, fixed point in the darkness of your closed eyelids, or at a small, steady star in the night sky. Now, in your peripheral vision, introduce something else, a faint, drifting cloud or a slowly moving dot on a screen. Keep your gaze absolutely locked on the central point. If you hold it long enough with enough stillness, something unsettling will occur. The moving object in your periphery will simply vanish. It will fade from existence, erased from your conscious perception, only to blink back into view a moment later, as if your reality had a temporary glitch. This is motion-induced blindness. It's a powerful visual illusion that reveals a critical function of your brain. It is not a passive camera recording the world. It is an active editor, and its primary rule is to ignore what it deems irrelevant. In this scenario, your brain receives two conflicting signals, a command from your will to fixate on a static point, and sensory data of a low-contrast, predictable motion in the periphery. Faced with this conflict, your visual system makes a choice. It prioritizes the focus of your attention and begins to literally filter out the unchanging, predictable noise of the peripheral motion. The object is still on your retina. The data is still coming in. But your conscious awareness is denied access to it. It's a dramatic example of a process that happens every second of your waking life. Your brain is constantly discarding the vast majority of sensory input. The feeling of your clothes, the hum of the refrigerator, the sight of a stationary bookshelf, to free up resources for what might be new, important, or threatening. Motion-induced blindness makes this editing room visible. It shows you that at any given moment, you are living in a profoundly abridged version of reality, curated by a silent editor who believes it knows what you need, and more importantly, what you don't. The logic seems straightforward. We do favors for people we like. Therefore, if we do someone a favor, we must already like them. But human psychology often dances to a more counterintuitive rhythm. Enter the Benjamin Franklin effect. The founding father and polymath famously noted that if you wanted to win over a difficult colleague or rival, you should not do them a favor. You should instead ask them to do a favor for you. The result, he observed, was that the person would subsequently like you more. Modern psychology confirms this reversal. When we perform a favor for someone, especially if it's a conscious, voluntary act, our brains engage in a subtle act of self-justification. Why did I just help this person? The mind asks. The simplest, most comfortable answer is not because I was pressured or for no reason, but because I like them, because they are worthy of my help. Our attitudes shift to align with our actions. We rationalize our own behavior by increasing our fondness for the beneficiary. It's a twist on cognitive dissonance, where our mind rewrites the narrative to make our actions make sense. This effect upends a common social strategy. We often try to earn liking through service, but the deeper psychological lever is to induce liking by gracefully receiving it. It suggests that the act of giving doesn't just flow from goodwill, it can also be its source. To allow someone to help you is to offer them a gift as well, the gift of liking you more. It's a quiet, powerful reminder that in the economy of human relationships, sometimes the most generous thing you can do is to ask. Walk into a friend's house for the first time and you are immediately enveloped by its unique scent, a signature blend of cooking, pets, candles, and life. To you, it is distinct and noticeable. To them, it is nothing. It is the smell of absence. This is olfactory fatigue or olfactory adaptation, your nose's remarkable ability to essentially turn itself off to a constant stimulus. Unlike your eyes or ears, which continuously report the same sight or sound, your olfactory receptors are designed to be novelty detectors. When a scent molecule binds to a receptor, it sends a signal to your brain: new smell. But if that same molecule continues to bind minute after minute, the receptor stops responding. It declares the signal to be background information, permanent, unchanging, and therefore irrelevant to your immediate survival. The scent hasn't disappeared from the air. Your conscious access to it has been deliberately revoked. Your brain, in its ruthless efficiency, has decided you no longer need to know. This is why you can't smell your own perfume or cologne after 20 minutes, why you become unaware of the subtle scent of your own skin, your own home. Your personal world is, in a very real sense, odorless to you. This constant resetting of your olfactory baseline is a gift. It allows you to walk from a fragrant garden into a pine forest and fully experience the new scent, untainted by the old. It clears the sensory slate so you can detect the truly important changes: the faint scent of smoke, the first hint of rain, the subtle shift that might signal food spoilage. You live in an ocean of scent you can no longer perceive, a personalized atmosphere that is both intimately yours and forever unknown to you. A silent reminder that your perception is always leaving something behind in order to move forward. Think of any list you've ever tried to memorize: a grocery list, the names of people at a party, points in a presentation. Now examine your memory of it. With striking consistency, you'll find that the first few items are crystal clear, and the last one or two are firmly anchored in your mind. But the items in the vast, sprawling middle, they blur, they fade, they slip into the fog. This predictable pattern is the serial position effect, a fundamental blueprint of how your memory works. It's composed of two distinct forces: the primacy effect. The first items benefit from your full, undivided attention. They enter an empty stage and get rehearsed and consolidated, securing a strong position in your long-term memory. Then comes the treacherous middle, where attention wanes and new information begins to overwrite what came just before in your short-term mental workspace. Finally, the recency effect. The last items are still clinging to the fresh, easily accessible shelf of your working memory. They haven't been pushed out yet. This isn't a flaw, it's an architecture. It reveals memory not as a uniform storage unit, but as a dynamic system with a privileged entrance and a fragile temporary holding bay. Your mind prioritizes what comes first, assuming it's foundational, and holds onto what came last, assuming it's most immediately relevant. Everything else exists in a competitive, vulnerable space. So the next time you forget the middle item on a list, understand it's not a personal failure. It is simply your brain, following its ancient and efficient protocol, deciding what, in the endless stream of experience, is most worth saving from the tide of everything that follows. You climb a familiar staircase in the dark, your feet moving with unconscious confidence, each step a perfect, predictable lift and fall. Your body knows this rhythm down to the millimeter. Now, imagine one step is just a centimeter taller or shorter than the others. Your foot, expecting the familiar, meets the unexpected. The result is a jarring stumble, a sudden flood of awareness, a visceral sense that the world itself has betrayed you. This is proprioceptive recalibration, or more accurately, its shocking failure. Proprioception, your body's silent internal map, is not static. It's a live, constantly updating prediction engine. With every repeated action, like climbing your home stairs, your brain builds a precise motor script and a sensory expectation. It predicts the exact amount of force needed, the precise angle of your ankle, the specific moment of impact. This automation is a marvel of efficiency, freeing your conscious mind from micromanaging every movement. But when reality deviates from the prediction, the system glitches. The mismatch between what your body predicted and what it feels creates that profound sense of wrongness. The stumble is more than physical, it's cognitive. It's your brain's alarm bell screaming, the model is incorrect. The world has changed. In that split second, you are violently ejected from autopilot and made acutely aware of your own body and its negotiation with gravity. It's a humble reminder that your graceful, effortless movement through the world is not a given. It is a fragile, ongoing agreement between your internal map and external reality. And it only takes 1 centimeter of difference to show you the intricate, invisible dance you perform every moment, a dance you only notice when you miss a step. In one of the most heart-wrenching and bewildering disorders of the mind, a person looks at their spouse, their parent, their child, and sees a perfect physical replica. The face is identical, the voice is the same, the memories and mannerisms are flawless. Yet with absolute, unshakable conviction, they know this is not their loved one. They believe the real person has been taken, replaced by an impossibly perfect imposter. This is the Capgras Delusion. Neuroscience suggests it is not a failure of recognition, but a terrifying break in the emotional symphony of perception. When you see someone you love, two pathways in your brain activate in harmony. The first identifies the face. This is my mother. The second, rooted through the limbic system, delivers the warm, familiar emotional glow, the feeling of connection. This is my mother. In Capgras, the first pathway remains intact. The person can intellectually identify the face. But the second pathway, the emotional connection, is severed. The brain receives the visual data but is met with a chilling internal silence. No warmth, no familiarity, no love. Faced with this dissonance, a known face that feels profoundly unknown, the conscious mind, desperate to make sense of the void, constructs the only logical explanation it can fathom. This must be a stranger, a duplicate, an imposter. The delusion is a tragic testament to the fact that we do not know people by face alone. We know them by the feeling that accompanies their face. When that feeling vanishes, the person, no matter how visually identical, vanishes with it. Capgras reveals that at the core of our deepest relationships is not just memory or sight, but an invisible thread of felt emotion. And when that thread is cut, the person on the other end, in the most real sense possible, simply ceases to exist. You're not at your desk, not straining for an answer. You're in the shower or on a long walk or washing dishes. Your hands are busy with a simple, repetitive task, and your conscious mind is adrift, idle, almost bored. And then from nowhere it arrives. The solution to a problem that hours of focused effort couldn't crack. A creative connection, an insightful idea, a sudden clarity. This is the shower thoughts phenomenon, and it's not random luck. It's the sound of your brain's default mode network finally getting to work. When you focus intently on a task, your brain engages a focused, goal-oriented network. But when you enter a state of low-demand, automatic activity, that network quiets down. In its place, the default mode network activates, a web of regions associated with daydreaming, memory consolidation, and self-referential thought. This is your brain's background processing mode. Freed from the constraints of direct problem-solving, it begins to make distant, associative connections. It sifts through the fragmented data of your day, your memories, your unsolved puzzles, and allows them to combine in novel, unexpected ways. The insight feels like it pops in, because the conscious, directive part of your mind wasn't supervising its creation. It was generated in the workshop of your subconscious, in the quiet hum of mental meandering. The shower, the walk, the mundane chore, they aren't distractions from thinking. They are the ideal conditions for a different, deeper kind of thinking. They provide the blank canvas upon which your mind's internal connections can finally paint themselves. So the next time you're stuck, the most productive thing you can do might be to step away, to engage your hands, and to let your thoughts, like water, find their own path. You've waited in line for an hour for a mediocre restaurant. You've sat through half of a terrible movie because you paid for the ticket. You've poured years into a failing project or relationship because you've already come this far. This powerful, often painful, impulse is the sunk cost fallacy, the tendency to continue an endeavor once an investment in money, effort, or time has been made, even when the rational choice is to cut your losses and walk away. The fallacy lies in allowing past costs, which are irrecoverable or sunk, to dictate future decisions. Logically, only future benefits and future costs should matter, but emotionally we are haunted by the ghost of our past investment. To quit feels like making that past investment a waste, an admission of failure. So we double down, throwing good money, time, and energy after bad in a desperate attempt to validate the original, now lost, cost. It's a battle between the rational, forward-looking planner and the emotional, loss-averse storyteller inside us who hates an unfinished narrative. We want the story to be, I struggled, but it was worth it in the end, not I struggled, and it was all for nothing. The sunk cost fallacy is the price we pay for being creatures who weave our lives into coherent stories. It shows that our decisions are rarely cold calculations. They are deeply human attempts to make peace with our past choices, to force the universe to honor our efforts, and to avoid the hollow ache of wasted time. It is the triumph of hope over evidence, of narrative over logic, and a reminder that sometimes the hardest thing to let go of is not what we're moving toward, but what we've already left behind. You watch a character in a film bungle a public speech, fumble a romantic confession, or commit a painfully awkward social blunder. Even though you are safe in your seat, a physical cringe washes over you. You might look away, cover your eyes, feel a knot in your stomach, all for someone else's humiliation, often someone who isn't even real. This is vicarious embarrassment, also known as Fremdschämen in German, a word for the alien shame we feel on behalf of others. It's a profound testament to the power of our social and empathic wiring. When we witness a social norm violation, our brain doesn't just observe, it partially simulates the experience. Our mirror neurons fire as if we were the ones in that mortifying moment. We don't just understand their embarrassment. For a fleeting second, we share it. This reaction is deeply tied to our status as a hypersocial species. Our survival has long depended on maintaining social bonds and understanding group dynamics. Witnessing a breach in the social fabric triggers our own alarm systems about belonging and reputation. It's as if our neural circuitry practices the emotional consequence, a warning shot to keep our own behavior in check. The fact that we react so strongly to fictional characters reveals the automatic, subconscious nature of this process. Our empathy doesn't pause for a reality check. Vicarious embarrassment is the shadow side of our profound capacity for connection, proof that we are linked so deeply to others that we can literally feel their social pain, a silent, shared wince across the space that separates us. Ask an older adult to recount the story of their life, and you'll notice a curious pattern. While recent events may be clear, there will be a disproportionate flood of vivid, detailed memories from a specific chapter, their adolescence and early adulthood, roughly between the ages of 10 and 30. This clustering is called the Reminiscence Bump. It's not that life was objectively more eventful then. It's that our brains are wired to prioritize and solidify memories from this formative window. This period is the crucible of identity formation, a time of first loves, profound friendships, major life decisions like college, first jobs, leaving home, and intense emotional experiences, both positive and negative. Our brains, in the process of constructing a stable sense of self, tag these experiences as foundational. They are the raw material from which our life narrative is built. The novelty, emotional intensity, and self-relevance of these events cause them to be encoded with extraordinary depth. Later in life, when we search for who we are, our memory retrieves these cornerstone experiences. The reminiscence bump ensures that the person we became is anchored by a rich tapestry of memories from the time we were becoming. It is the psychological reason why the music of our youth feels so timeless, why smells from that era can be so powerfully evocative. It's not mere nostalgia. It's the architecture of autobiographical memory, ensuring the most defining chapter of our personal story is always the best remembered. In a hospital room, a patient with damage to the primary visual cortex insists they are completely blind in a portion of their visual field. They see nothing but a void. Yet, when a researcher asks them to guess, to point to where a moving dot might be, or to reach for an object in that blind space, something impossible happens. They perform with accuracy far beyond chance. They can navigate a cluttered hallway, avoiding obstacles they swear they cannot see. This condition is called blindsight. It is one of the most philosophically startling phenomena in neuroscience, revealing a profound rift in the mind. The damage is to the cortical pathway responsible for conscious visual perception, the one that creates the picture you experience. However, older, subconscious visual pathways, which travel to different brain regions involved in movement and spatial awareness, remain intact. These pathways process visual information about location, motion, and broad shape without ever generating a conscious image. The person's eyes are taking in the data, and parts of their brain are using that data to guide action, but the experience of seeing never reaches the theater of their awareness. Blindsight presents a radical dissociation between knowledge and experience. The patient knows where the object is at some level. Their hand can find it, but they have no feeling of knowing. It suggests that consciousness is not the totality of mental processing, but a specific, and sometimes optional module. You can act intelligently on visual information without ever seeing a thing. Blindsight is a quiet, clinical demonstration that much of what we call seeing happens in the dark, behind the closed curtain of our own awareness. You read a personalized horoscope or a personality profile. You have a great need for others to like and admire you. You have a tendency to be critical of yourself. At times you are extroverted, affable, sociable, while at other times you are introverted, wary, reserved. It feels uncannily accurate, as if it were written just for you. This is the Forer effect, also known as the Barnum effect. It is our powerful tendency to accept vague, general personality descriptions as uniquely personal and accurate, especially when we believe they have been tailored for us. The statements above are purposefully broad and apply to almost everyone. They are statements of universal human experience, the desire for social approval, internal self-criticism, shifts in mood. Our minds, however, are pattern-seeking and self-centered engines. When presented with such statements, we engage in a process of subjective validation. We selectively focus on the parts that match our self-image and memories, ignoring the parts that don't, and we mentally fill in the vague gaps with specific details from our own lives. The source's perceived authority, an astrologer, a psychologist, a sophisticated algorithm, heightens the effect. The Forer effect is the psychological engine behind the success of astrology, some personality tests, and cold reading techniques. It's not a sign of gullibility, but of our deep-seated desire for self-understanding and coherence. We are so eager to see a clear reflection of ourselves that we will happily project our own details onto a fuzzy, generic template, creating a perfect match where none specifically exists. During a conversation, you may find yourself leaning forward when they lean forward, crossing your legs when they cross theirs. Without thinking, your speech pattern might soften to match theirs, or you might pick up a slight inflection from their accent. This is unconscious mimicry, or the chameleon effect, the automatic, non-conscious imitation of another person's postures, gestures, facial expressions, and speech patterns. It is one of the most fundamental and subtle mechanisms of social bonding. This behavior is driven by mirror neuron systems and is deeply rooted in our evolutionary past as a pro-social adaptation. By subtly mirroring someone, we create a nonverbal rapport, signaling I am like you, we are in sync. This builds trust, fosters liking, and smoothens social interaction. Remarkably, the person being mimicked usually feels more positively toward the mimicker, without ever being aware of the specific behavior. The mimicry is a social glue, operating beneath awareness. It explains why close friends and couples often develop similar mannerisms over time, and why people in a group can converge on a shared emotional tone. It's also why you might leave a conversation with someone from a different region and notice a trace of their accent in your own speech. Unconscious mimicry reveals that our identities are not rigid, self-contained entities. They are permeable, fluid, and constantly, subtly adjusting to the social environment. We are always, in small ways, becoming a little bit like the people we are with, weaving an invisible tapestry of connection through the silent, automatic language of our bodies. An idea is mentioned once, and it passes by like a leaf on a stream. It's mentioned again in a different conversation, and you note it with mild curiosity. Then you see a headline, overhear a clip on the radio, catch a fragment in a social media feed. Soon, without you ever seeking it out, the idea feels omnipresent. It begins to sound not just familiar, but plausible, then probable, then simply true. This self-reinforcing cycle is known as the availability cascade. It's a social and psychological process where a concept gains increasing plausibility and perceived importance through its rising repetition in public discourse, not through an increase in actual evidence. The mechanism is twofold. First, the sheer cognitive availability of the idea, the ease with which it comes to mind, tricks our brains. We use a mental shortcut called the availability heuristic. If we can recall something easily, we assume it must be common or true. Repetition makes recall effortless. Second, as more people begin to discuss the idea, a bandwagon effect takes hold. Individuals, perceiving the idea as gaining social consensus, become more likely to adopt and repeat it themselves, further fueling the cycle and silencing private doubts. The cascade isn't necessarily about falsehoods. It can amplify genuine concerns or accurate information, but its power lies in its ability to detach perceived truth from evidentiary truth. It reveals how our sense of reality is not built solely on facts, but on the repeated echoes of those facts, or their approximations, in the chambers of public conversation. The idea gains a momentum of its own, a truth by acclamation, washing over the quiet, complex landscape of what is actually known. It is the sound of an idea becoming real, not because it is, but because we have all heard it together enough times.